Hello, Katerina.
Yes, hello. Hi, can you hear me well?
Yeah, I can hear you well.
Perfect, I can hear you well too. And I put the link up. You can check if you can click it. And
I don't see the presentation.
so above our profile pictures, there's a link that you can click. Do you see? There's like a little picture with the label and
Little picture of
of the presentation, and then there's, if you click on that, it says go to link, and then
hold on 1 second. The presentation, I don't see. So first it's I saw my picture, then my name, then audio settings, notification, online friends, topics, language. Which one is the presentation thing?
Are you on the desktop?
I'm on the laptop.
Oh, okay. I'm not sure how it is. I cannot open the laptop to check how it looks like. So do you see just your name, or do you also see my picture and Victoria?
I saw your picture, my picture, and then followed by the speakers and some other people's picture here.
Okay, so do you see above our pictures a link that you can click?
Oh, I see. There is a
Yes.
okay, yeah.
So yeah, so just this won't be a screen. So this is not a screen share. So how you're opening up the
No,
presentation,
I
that's
just
how also the audience will open it up. So it's really helpful to refer to which slide you're on when you
oh,
switch.
I see. Now I opened the slides already.
Okay, yeah, perfect. Yeah, so but everyone has to open the slides by themselves basically. So
Okay.
yeah, just a reminder to, like, when you switch to the next slide, to tell people,
But
let's
when I open it, it doesn't show single slide. It show two slides on the same screen.
yeah, it's kind of yeah. So yeah, the display is a little bit different than on the it's not like a full screen display.
I see. I see.
But you have the slide numbers, so you labeled them, so you could
But how
just.
about the animation? Then I can't show the animation, right?
Yes, it should work, the animation. On which slide number do you have?
Most of the slides I have like the items come out one by one.
Oh, yeah, that maybe it doesn't work here. I don't see it working that way.
Okay, okay. If that's so, that's okay.
I didn't know that.
So you don't have the function like share a screen, sort of that kind of function.
No, we don't have that here.
Hmm.
But so the
So,
thing is that we don't have the screen share, but this link will. So we are recording the session, and for people that are, where it's in the middle of the night right now or so on, when they listen to the replay on the Clubhouse app, they can still. So the links are still active in the replay, and also the links in the chat with people share links. So while they are listening, they can do the same thing we will do, to click on the presentation and then follow along while you speak. That's what I like about this type of recording, since we have people really all over the world, and there's never a time where everyone is awake or able to attend. So
I see.
yeah, and in other we
So
don't have.
you said that everyone else, everyone online, they just basically, if I tell them which slide I'm on, they just follow along. They have to click their computer to get to that slide, right?
Yeah,
Oh,
exactly.
okay, okay. All right, got that.
And how was your week? Happy Friday.
Oh yeah, happy Friday. Finally, it's Friday. I came back from Los Angeles. I was in Los Angeles for 3 days. I came back Wednesday afternoon. So I'm only in office yesterday and today.
Oh, nice.
Yeah.
Was it for work or for
Well, my son is going to have his first baby. They had a baby shower, so I was
Oh,
there.
exciting.
Yeah,
Congratulations.
yeah. Thank you.
Is it the first one? Yeah,
The
you said
first,
the first.
yeah, that's the first of. My son is the oldest child of the family, and obviously this is his first. It's first baby, so my first grandbaby.
That's wonderful. That must be so exciting for
Yeah,
you.
it is exciting. So that's why we went to Los Angeles for the baby shower.
So yeah, that's a good week. So how long do you still have to wait?
Oh, it's not too much longer. Today is 19th already, and their due date expected date is September 16th. So less than 4 weeks.
Oh wow, that's really close. That's nice.
Yeah. Hmm.
It's a nice time to have a birthday. No, don't
Yeah.
you
Yeah.
think it's a nice time of the year to have your birthday?
Right. Right. September.
Yeah.
It's three generations all are in September. Myself is in September. My son was September, and now the grandbaby will also be in September.
Oh wow, that's amazing. That's that will be a huge birthday celebration month.
That's
And
right.
it's
Yeah.
yeah, it's kind of in the middle of the year. I like that.
Right. So each generation is earlier. I according to the calendar year, I was born in uh, 25th of September, and my son was born on 23rd, and the grandbaby will be sometime in September. Definitely will be before my son's birthday. So each generation is a few days earlier.
That's so interesting.
Yeah, it is.
That's very curious. That's well. I hope everything goes well for the mom. And
Yeah,
yeah, I wish you all the best and all the luck for your grandchild.
yeah.
That's
Thank you.
very exciting.
Yeah. Thank you for reminding me this because I didn't have it on my calendar. So luckily, I'm
I'm
in
glad you
today.
still came and made the presentation. That's amazing in such a short time.
Well,
Thank you for
I
doing that.
had it before, and I just needed to modify the slides, add more, take out more, that kind of adjustment.
Hey, hey, hey. How's everybody doing? Hello, Dr. Shin. Welcome to Science Society. Welcome to Clubhouse. How are you doing?
I'm fine, thank you. This is Zifeng Ren.
Oh, this is who? How do I say your name?
Yeah, Zifeng Ren.
Zufan Ren. Okay, that's right. You got Dr. Shin, Dr. Ren. So you're Dr. Ren, right?
Yes, I don't think Professor Gang Chen will be on today. He didn't reply to me.
Gotcha. That's okay. So, Dr. Ren, are you also in Houston?
Yes.
Whereabouts?
I'm at the University of Houston.
Nice, nice. I'm in Houston as well, dude.
Oh, I see. So you are in
Yeah.
which part of Houston?
I'm right right now. I'm floating around Houston, right? So I took off for a while to India. We built this oxygen concentrator, and the whole world started using it, during COVID and stuff like that. So, but I'm back right now. I'm in staying
Oh,
at a hotel at the Marriott over in Westheimer and Beltway. You know?
I see. I see. Yeah,
Yeah,
West Ham.
yeah,
I
yeah,
I lived in Galleria area for 1 year there.
yeah. The guy. So you're like where in the guy like right there, 610 and Westheimer.
It's very close there. Yeah,
Yeah, yeah. Are you in the loop or outside the loop?
I was outside the loop, and then just rented it for 1 year, and then bought my house here in Houston, and then I moved to Pearland. Right now, I'm living in Pearland.
Oh, in Pearland. Okay. Yeah. So you're down there at 288 and Beltway and stuff, right?
Exactly. Right after Delta 8, and then take off on Route 518. Very close. In fact, very close to 288.
Yeah. And for those of you that don't know, Houston is massive. Okay, just so you guys know, it's like a huge land mass. It's massive. We got 3 loops around us. There's the 610 loop, and then we got this Beltway loop further out, and then I think the uh, was it the
Number
99
6.
loop? How long? That thing's like what, 270 miles or something crazy? Like, how big is that loop? You know, or what is
It's huge.
it's crazy. It's crazy,
I
right?
think
I
for
mean,
Delta 8, if you drive around the loop, you need like 2 hours definitely.
yeah, for sure, at least
And
2 hours.
then, but for the third loop, number 6, you probably need like 3 to 4 hours drive around.
Oh, I think you need more than that. Oh, that's right. 6. You got Highway 6, and then you got 99. I forgot. We got 4
Oh,
loops around us, dude. You know,
right.
we got 1960. It turns into 6. It's interesting. Yeah. So, Dr. Ren, here on Clubhouse, right? Like, so think of it as you're kind of presenting more likely to like your peers, right? And what I mean by that, like, especially in the science side here, you got a bunch of other PhDs and doctors and entrepreneurs and like techie people that are interested in science and like to collaborate and whatnot. So it's consider it like it's a fun group, like a fun gathering. It's a little different, where um, like the hope. Imagine you're presenting, right? Like in your living room. That's the best way. Like you got some friends over at your place, and you're just hanging out. And everybody's hanging out, maybe around the fire chat, like a fire chat kind of thing. And you're at the clubhouse, and like you got your neighborhood in Pearland. You got the little clubhouse. We're all hanging out, and you're presenting some stuff to like your friends and things, right? And you got some food over there because everybody's like sitting down eating something, probably laying down, right, at their home, right? So it's like a very comfy kind of environment. So I just kind of want to give you that it's different. It's different than typical presentation. So and if you want, like
Very different. In fact, uh,
yes,
since pandemic started, I have been presenting online on different platforms. One time, I was, before pandemic, I go around the world to present. Most of the time, if you get audience like if you get like 200 people, you say, "Wow, so many people today." But that's not nearly as many as online. In middle of 2020, I gave a talk at that time. We had 135,000 people online for that talk. But the thing is, even though you have so many audience, but you don't have the passion, you are talking to a computer, talking to a screen, which is totally different from you talk to real people. So we prefer to talk to real people.
Oh wow. Yeah.
yes, for sure. So we welcome you, and we're honored to have you do the presentation today. What would be super cool, and I think you'd have fun doing it too if you want. Like maybe after your presentation, all of it, like a bunch of us are going to jump back into like a little pillow tribe room, and we just like collaborate, and we would love to maybe basically expand upon what the future could look like. Like you'll have a lot of brains in there. It'll be a lot of fun if you have time, right? So whatever time you got, you know, we just kind of look forward to hearing you present, but also adding value by hopefully giving you some ideas and different things that you go back home with too. So that's with that said, I think we should go ahead and get started. So the floor
Sure.
is. I'll
Yeah,
pass it to
thank you.
Katerina first. Go ahead, Katerina.
Yeah, so welcome to Science Society, Dr. Ren. It's such an honor having you here. And yeah, before we start, let me give the audience a little bit of an introduction so they get to know you a little bit. Dr. Zifeng Rang, he's an Anderson Chair Professor in the Department of Physics at Houston in the Science Center for Superconductivity. And He did his bachelor in material science and engineering department of mechanical engineering at the Sichuan Institute of Technology in Chengdu, China, and his master's in science and engineering department of mechanical engineering in Huazhong University of Science and Technology in Wuhan, China. And then he did his PhD in condensed matter physics, Institute of Physics at the Chinese Academy of Sciences in Beijing, China. And Dr. Ren, his research is focused on high performance thermoelectric materials and finding catalysts for water splitting, and a nanosheet for enhanced oil recovery, thermal management, to find efficient cooling materials and thermal storage, superconductivity, solar energy conversion, and flexible transparent electrodes. And yeah, so it's all really, those are all really interesting fields of research. And before we start, I would like to ask you like a couple of questions. And when did you kind of decide or had an interest in going into science and doing this, like, life, having this life in science? Was it something you always wanted to do? Was it maybe a teacher or book you read or something that excited you to go into and make your life about science?
That's a very interesting question. When I was growing up, at that time, that was back in 1970s. At that time, in China, of course, the condition was very bad. My parents, they were illiterate. They never had a single day in school. They were farmers, and the whole goal at that time is just try to get to college or any school, professional school or college, and then get a work instead of a work in the cities. Doesn't matter, small or big. Instead of working on the land as a farmer, that's the only goal at that time. But of course, after I got into the college and slowly get into different kind of fields like engineering, science later on, and just follow the flow. Really, I didn't have any big goal like others. Some people, when they were young, they had a dream, become a scientist, become a astronaut, become whatever. Those kind of big professions. I didn't have that kind of thing. Just follow the flow. And my philosophy, lifetime philosophy, is doing things, do the best of whatever comes to you today, and do the best for today, and then look forward for tomorrow. And no big plans for too much down the road, because that's out of reach anyway. That's my part of my life.
That's, I think, a really great. That's a great approach to do that, to manage life. I think it's only so much we can control. So doing our best is the thing we can control. That's a very interesting story. And how did you come about this project or going also into this type of field of technology, physics, engineering? Yeah, how did you then ended up here discussing about this project? Basically, thank you.
Yeah, that's also very interesting. As I told you that my career, I started as a farmer's son and then got into college. All my degrees, as you introduced, were in China, and I came to this country in 1990. Did my postdoctoral fellow work at SUNY Buffalo. Then I moved to Boston College as a professor. At that time, I was mainly studying, carbon nanotubes, superconductors, the carbon nanotubes, which I'm not going to talk about today. But at that time, I basically opened up a new field for the world, how to grow 9 carbon nanotubes for flat panel displays, which was very promising at that time. And then, of course, later on, I moved into thermoelectrics, and then after I came to Houston back in January 2013, and I branched or broadened my research to many more fields, which I'm going to talk about a little bit in my second slide anyway. So basically, all those things I follow, sort of just like my life. Do everything the best for today, and then look forward for tomorrow. At the same time, for research field, it also the same thing. And then whatever I have, I do the best, and then try to look for new opportunities. If there's anything new, then I feel that I have the capability, also the facilities, and I start to get into it. But the first question always I ask myself is, can I do this uh, very well? Sort of very well. I'm talking about to become the best in the world. If my answer to myself is, oh no, that's probably I'm not going to be the best in the world, and then I said, forget it, I'm not going to get into that. Unless I can become the best in the world, I say, okay, I'm going to get in. So for this specific project, Boron Arsenide, we're going to talk about today, is in fact happened right after I moved out of Boston College. My former colleague, Professor David Bruidel, called me saying that, Zhifeng, I just recently calculated a new material which could have thermal conductivity higher than diamond. I said, wow, that's great. Diamond is so much difficult to make it a large size, even though it does have high thermal conductivity. But really, you can't make it in large size nor use it for large scale. And if you could have something else, could have thermal conductivity like higher than diamond, that would be very interesting. So I immediately jumped into look into how to make it. That's how ended up with the recent a few years the kind of research and the work on boron arsenide, which I'm going to talk about more detail.
Yeah, thank you so much for sharing this background story with us. It's so impressive, and I'm so glad you have these capabilities and that you follow those principles, and humanity gets to be able to use all your discovery. So thank you for following that path. And yeah, the stages are yours now for the presentation. So feel free to yeah, I don't know if you prefer for questions to come along in between, or if you want to have like a discussion session after. That's really up to you. We'll help you moderate and whatever you think makes more sense for you. And yeah, thank you.
Okay, thank you so much, Katarina. Thank you all the audience wherever you are. This is a maybe for some of you, it's not a really convenient time, either too early or too early in the morning or too late in the evening. But anyway, thank you. So what I'm going to talk today is about boron arsenide single crystals. So first, I would like to thank all the collaborators, my former postdocs like Dr. Fei Tian, Hao Dan Sun, who are working as professors in China universities, and also my former student Guitar Gimage, who is working in NAM. I think it's a NAM research lab in California, and also my current student Feng Jiao Pan. And then, of course, I would like to thank Professor David Bruidel at Boston College, who theoretically predicted this material with high thermal conductivity. I would like to say a few more words on this. some of you in the audience know that research is our theoretical part, also the experimental part. Very often, the best theories that would be you predict something and the experimentalists try to make it, and then try to make it which prove the theory is right or wrong. Of course, that doesn't happen very often. Only very, very small fraction of the theories that can do that, predict something and then later be proved by experiment. Most of the theoretical work is try to explain what experimental work is, and how to interpret the data, not for prediction. Both are necessary. What I'm trying to say is for the world. And then I also would like to thank Professor Gang Chen at MIT, who has been my very long time collaborator. And then turns out also we came out from the same university in China when I was a master degree student at the Huazhong University of Science and Technology. And luckily, I have been in Boston. He has been in MIT for many years. So we have collaborated for a very long time. And we published probably now close to 200 papers together. And then another collaborator I would like to appreciate is the Professor Shi Li at UT Austin, who has been studying boron arsenide with us. And then for the audience, if you can go to slide 2, second slide. And what I would like to use this opportunity to tell you a little bit on my current research areas. Katerina has alluded a little bit. So here I'm telling you that my research work covers like high performance thermoelectric materials. Mainly, we are looking at the figure of merit, how efficient these thermoelectric materials can be for power generation and also for cooling applications. In fact, a lot of you are using probably thermoelectric devices, but you don't know they are thermoelectrics. For those of you, if you have a high-end car, a back seat, if your car seat, you turn on your engine very quickly, your seat is very cool. That cooling is by thermoelectrics, not by your compressor, your air conditioning system in the car. It's different system. And also, some of you have wine coolers. You put a wine on the in the cooler, which is thermoelectrics. And also, not of hotels nowadays, the refrigerators were thermoelectrics, which does not make any noise. Oh, by the way, Katerina, if the audience wants to raise questions anytime, please interrupt me.
Then I have a question I would love to interrupt with. Thermal
Sure.
electrics, I can reverse thermal electrics by excess heat pools and capacities and generate electricity too, right, with this?
Yes.
So if I had say a data center full of excess heat,
yeah,
what I
exactly.
guess carry on with what might be the possibilities with your research due to having a pool of available heat.
Exactly. So thermoelectric materials, there are two, well, in fact, three functions. One function is you use electrical power to cool one side, and then the other side will become hot. It's sort of a heat engine. And then say, for example, in the summertime, if you put your thermoelectric cooler on the window, you take out the heat from your room and dump it outside. And then in the winter, you can reverse it. You can take the heat from outside and dump it into your room and as a heating. So that's two functions already. At the same time, in your data center, if you have a lot of computers consuming a lot of power, you generate temperature there, and then you can use your thermoelectrical device and convert that heat into electrical power. So thermoelectric is very versatile. And not only they are versatile with multifunctions, but also they don't have moving parts. They do not make any noise, and also their lifetime is very long. You can use it for 50, 60, or over 100 years for the same device.
50, 60? Because the current, I thought, read up on those thermoelectric cells were only 20 years.
Well, give you example. In 1950s, 1960s, NASA launched very deep space flying objects because they are so deep. They are out of the reach of the solar sun, the light from the sun, and they could not have any energy except they carried radioisotope materials on the flying object. Then they use thermoelectrics, convert those heat into electrical power to supply power to those deep space missions. And those objects, they were launched in 1950s, 60s. They are still working perfectly fine. Now it's already over 60 years. And the next phase, US, as you know this, US is going back to the moon. And the power in those flying objects to moon, they are going to use the also thermoelectrics. Does that answer your question?
It does. Are there any particular heat gradients that you require to be best optimized? Say, like, what's the temperature differential that would be great for that?
So for that, you obviously we have different kind of temperature gradient. For some, like your data center, you are looking temperature gradient probably somewhere 50 degrees, because your temperature will not be too much higher.
But if
However,
it's best to use thermal pumps to aggregate it, it could be worth doing that for efficiencies on the conversion.
of course, if you can increase the hot side temperature, and your efficiency will be higher. But of course, in order, when you pump the heat to raise the temperature, you consume energy. So at the end, you may not benefit at all from the energy recovery point of view. And of course, for other heat source, you could have, like, say, hot side a couple hundred degrees C or 1,000 degrees C, depends on whatever your heat source temperature it is. And then we, as a researcher, we have studied a different kind of thermoelectric materials, which are suitable for different temperatures. Overall, the general rule is the higher the heat source temperature, and then you are going to have the higher efficiency and more energy recovery. So that's the general. So we do have different materials, different devices suitable for different temperatures. Okay.
Hey, I have a question about the prediction of the heat conductivity of boron arsenide.
Right.
So, first of all, what kind of methodology was used in this prediction?
That was the first principles calculation.
Okay, DFT.
Well, DFT, or different kind of ways they use methods. The DFT, I think they also use other methods. Yeah.
Okay. So maybe a bit of a technical question, but with all these first principles calculations, one of the big drawbacks is actually getting results at finite temperature. And I think there's this Seebeck coefficient, which characterizes how efficient a thermoelectric is. So I was wondering, I mean, from DFT, what you really get is the ground state density of a material, electron density. So going from that, how would you calculate the Seebeck coefficient or its thermal conductivity?
Right. For the Seebeck, well, first of all, for the thermal conductivity calculation, when the materials are complicated, which requires a lot of calculating power. So thermal conductivity is very complicated physical parameter. It is affected by a lot of things. Many is photons and then also charge carriers. The photons, you have optic photons, you have acoustic photons, and then different branches, and then you have photon scattering, 3 photons, 4 photons, all sorts of those things. which I'm going to talk about a little bit later. For the Seebeck coefficient calculation, obviously you need the band structure. You need also to know the carrier concentration. You also need to know mobility, all sorts of those things. And again, it's pretty complicated. But nowadays, there are so many people have developed very good calculating methods. They can pretty accurately predict the Seebeck coefficient, thermal conductivity, what sort of physical properties. So does that answer your question?
Yeah, thank you.
Okay, so then let me continue if no more other questions. So my second project I'm doing here is materials, basically finding or invent new materials with ultra high thermal conductivities and also ultra high carrier mobilities. In this particular case, we are studying boron arsenide, single crystals, which is in fact the bulk of today's talk. I'm going to go into more detail on how to make them, how to characterize them. And then third project that my group is doing is we try to find materials for oil recovery. I know nowadays we are, as a society, we are very much look forward to have clean energy sources instead of oil, gas, or coal. But nevertheless, let's face the reality. The clean energy will not be able to support the society now. Probably will not be able to even in 10 years' time. I know eventually we are going to move into clean energy, but before, I normally call it the clean energy is our promised land. But before we reach our promised land, we still need that bridge. So oil, gas, coal, all sorts of those kind of fossil fuels still will be very important, bring us to the promised land of the clean energy. But how to get oil out of the ground economically, environmentally friendly, all sorts of environmental benefit. I invented a sodium nano fluid, and which will react with water when I inject it into the oil wells. It will react with water, generate hydrogen gas, generate sodium hydroxide, also generate a lot of heat. All those are very beneficial for oil recovery. We are commercializing that technology very actively. The fourth field my group has been doing is the efficient catalyst. Really try to splitting water into hydrogen as an energy source. And also, of course, in some situations like in hospital, oxygen is also very useful. The reason we do that is we figure out in the future the best way to store energy would be, I think, batteries and also hydrogen. But how to produce hydrogen is very important. Currently, the industry has been using fossil fuels to either do gasification of coal or use the natural gas methane reforms called gas reform. But all those kind of processes, they use a lot of energy at its beginning, and also at the end, they produce a lot of environmentally unfriendly gas like carbon dioxide. That's not good. But however, water splitting, you generate hydrogen and oxygen. There's no negative things coming out, byproducts. And also that you can use, basically what I'm trying to think is use a wind power, solar power, and also very importantly is a grid power when demand is not there at the off-peak time. When you have a lot of electrical power, you don't know what to do with it. And then we can use the water splitting electrolysis to generate hydrogen. That's why I'm working on that. And then the fifth research territory I picked up, that was in right after the pandemic. And we know at that time, the COVID, COVID-2 virus is transmitted from people to people through air. So in order to eliminate the transmission or slow down the transmission, cleaning the air is very important. So which is why we invented a new filter that can be heated up to above 100 degrees C, which can instantaneously kill the virus, also with very high filtration efficiency. Our filter can filter any particles, including any viruses, bacteria, all those things. Anything size-wise above 0.3 microns at the efficiency 99.97% by a single pass. If you have, if the air comes from your room, again goes back to the filter, and then by 2 passes, basically, there's no any potential virus in the room, and it's very clean. And then the other research topic in my group is on superconductivity. Right now, I did my PhD study on superconductivity, and then after many years, I have not done research on superconductivity, but now I'm looping it back to superconductivity again. This time, I'm not doing any fundamental research on superconductivity, but try to use the existing superconductors for applications. And I have a grand view now to completely change the society, how the energy is transmitted, how the mass transport, everything. So my view is, I have a vision is try to modify the current highway system and use and then all the vehicles will be superconducting navigated. Instead of going in the future 75 miles per hour, we're going to go 400 miles per hour. And you're not touching the ground because you're suspended. You can go much faster, and also you use very little power to go forward. Give example, if since I'm in Houston, if I want to go to Los Angeles, the total mileage is under 2,000 miles. Now you have to drive 2 days to there if you drive. But use a new system, you can sit in your car, you don't do anything, fall into sleep, and after 4 hours, between 4 and 5 hours, and you're in LA, and you drive your car right off the highway and to wherever you want. And not only the personal cars, also the trucks, the buses. In this way, you don't have to, the traditional superconducting magnetic train. The train has a schedule. You cannot go anytime you want. But use a new system, you can go anytime you want. In order to do that, we need a lot of superconductors on the highway, and the superconductor will be cooled by liquid hydrogen. So in this way, your liquid hydrogen is being stored and cooled and stored and also transported along the way from Houston to LA or to New York. If you need hydrogen, you can get it out there. If you produce hydrogen, you want to inject it to the system, you inject it, and you get paid by the system. So that's hydrogen storage, hydrogen transport, and also a lot of electrical power will be transmitted through the superconductors, and then also stored there. And so this way, it's a one system. You have 6 functions. You have electrical power transmission and storage, 2 functions. You have clean energy hydrogen, liquid hydrogen transmitted and also stored. And also you have the people and goods moved, mass transit moved from place to place. Does not depend on the schedule, and you can go anytime you want, very fast, save a lot of money. So that's the research territories, research fields my group has been studying. And if you have any questions now, I can answer, or if you don't, I can go on to the really talk about it, boron arsenide.
So let me just real quickly interject real quick, Dr. Ren. First of all, let me say, dude, you're like you got to stay on Clubhouse, man. You're gonna love Clubhouse. The way you're speaking, right, and even the way you're navigating, like you're talking about a piece. If I have any questions, right, you're talking about the future and what cities could look like and be like. This is you're gonna love this place and the minds in here. So we're happy to have you on here, and like hang out. You could just put it in the background at times, especially throughout the day. Like the folks in here are great minds and. This is gonna be pretty fun. But during this time, hey guys, just let's do like housekeeping real quick. If you can all just, especially if you're new here, follow the club at the top, the little house, Science Society. Click that. Go ahead and hit follow. And if you can, at the bottom of your screen, where you see the little share button, right? Bottom left, the little arrow pointing up says 9 on there right now. I think so. We've had 9 people share, right? If everybody can just take a second right now and share this room on Clubhouse. I'm really pushing the sharing function here because if we want to get Clubhouse to like, how Clubhouse is, lots of debate rooms, lots of different things, this kind of information, science, it's collaborative, it's educational, it's productive, it's intentional, it's purposeful. Let's get more of this going around. And the way we do that is by sharing this so that others can come in, gather knowledge and information, and then also help, show and guide folks how to have nice, productive rooms. So thank you for that. And with that, I'll pass it back over to Dr. Ren. The floor is yours.
Thank you so much. Let me go back to the Clubhouse and then for the presentation part. Okay. So, okay, let's move on to slide 3. And as I said, what I'm going to present today is mainly on boron arsenide single crystals. I'm so sorry, I spotted a typo. Should be BAS single crystals, not same crystals. And then also I'm going to mainly talk about the thermal conductivity and mobility. Okay, let's move on the slide 4. So thermal conductivity, I alluded this earlier on already. Thermal conductivity is controlled by 2 parts mainly: electronic thermal conductivity kappa E, and also phononic thermal conductivity by kappa L. Electronic ones, it's very much related to the electrical carrier concentration. So basically, carrier concentration determines the electrical conductivity, which is why in materials like you have copper, silver, gold, aluminum, which has very high electrical conductivity, and then gives you thermal conductivity about like 400, around 400 at room temperature. But that's not really that high in comparison with like diamond. Diamond has over 2,000. And then, but the diamond thermal conductivity really comes from the phononic part, it's kappa L. Kappa L is related to like specific heat, the mean free path of the photon, group velocity, all sorts of those things clearly. Traditionally, high thermal conductivity of any crystals from the phononic part really determined by 4 factors. This is by Snack back in 1970s pointed out. The material has to be single, a very simple crystal structure like a diamond. Also, they has to have no anharmonicity. So that means the photon scattering has to be very low in the crystal. And also, normally it's a low average atomic mass. In the periodic table, like boron, carbon, those kind of light elements. Okay, and of course they have to have very strong atomic bonding. Otherwise, the heat is not going to be able to transmit it from lattice point to point. That's how they do thermal conductivity. And let's move on to slide 5. Here I'm giving you a table which shows that the thermal conductivity materials, now so-called high thermal conductivity materials, available in literature. So first, of course, is diamond. As you can see, diamond has room temperature like 2200 something, and then the other slash number 3400. That's the isotope pure. If you spend a lot of money, purify the carbon, instead of carbon 11, you can have carbon 12, and then you have either 11 or 12, and you are going to have higher thermal conductivity, but the cost is much higher. On the other hand, you have other materials like graphite, which also has pretty high thermal conductivity, but only in two directions, in the plane. Graphite are flakes, right? Perpendicular plane to the plane is very low, only a few. And then, of course, there is also one-dimensional materials, carbon. A lot of high thermal conductive materials related to no, small like carbon. Carbon nanotubes has a one-dimensional thermal conductivity over 6,000. And then, of course, you have also boron nitride, silicon carbide. All those either, if you really look at this, the not too many materials here is isotropic. Diamond is isotropic at over 2,000. Silicon is very low, only 140 something. And then graphite, carbon nanotube, cubic, boron nitride, they are all two-dimensional or one-dimensional. The thermal conductivity is low. And the next is really isotropic ones like copper, silver, silicon carbide. They are all lower than 500. So anyway, between 500 and 2,200, there's no single material has isotropic thermal conductivity in that range. So which is why anytime if you can make isotropic high thermal conductivity materials, it's going to be very interesting. So let's move to slide 6. This I'm going to show you, say, it's a periodic table. As you can see, I showed you the materials. Often high thermal materials are focused on boron, carbon, and nitrogen. A little bit like silicon, not much. And then any other heavy elements, materials made by heavy elements, normally thermal conductivity is low. So move on to slide 7. This is very surprising. Back in 2013, when my former colleague David Bruidel called me, told me saying that, Zifeng, I predicted through calculation, I found the boron arsenide could have thermal conductivity higher than diamond above room temperature, which is shown on the left panel. Wow, I was saying, this is unbelievable. If your prediction is true, and you are going to change the world. But nevertheless, how can we prove it? So first I asked him, why is this so? Then he told me, he also showed on this right panel, on this slide, he said that the reason for that is because the photon dispersion is very different for this new material. So normally you would not think boron and arsenic, because arsenic is heavy, and you have a light element boron, you have a heavy element arsenic. Normally thermal conductivity is not going to be high at all. Okay, but through his calculation, he said he found out that this material somehow is very strange. They have the optical photons, and also the acoustic photons separated by a big gap. That gap made the acoustic photon interference with the with optical photons is very small. So basically, 3 photons is only it's even not reachable to the optical. And then at that time he did not consider 4 photons. Which is why he said the high thermal conductivity is possible. So with that, and then we immediately started to try to look into how to make it. So let's move on to slide 8. So I started, doing research. Anything, if you want to do, you have to look at the literature to say who has done what in the past. And through literature research, we found that back in 1958, there was a paper. This is the full paper. The whole paper is this much, half a page. of the journal, and it says that this group was making 3,5 compounds, and he reported here boron phosphide and boron arsenide. So basically, he made this material and found the crystal structure is cubic structure and also X-ray diffraction, powder diffraction peaks for 2 materials, and that's all. The whole paper. It's amazing, without any other properties reported. But then, if you move on to slide 9, since after 1958 to 71, and more than 10 years, there's no second paper report anything on this material until this paper in 1971 says that, it is a semiconductor with a band gap about 1.6, 1.4 EV, and also with the mobility here says that anywhere between 100 to 400, very small, very low in fact. It's not too low in fact, but not very high, okay? So then after that, there's no other paper about boron arsenide. So then we started looking into this single crystal growth. And when we looked into it, we found that, let's move on to slide 10. We found it's very difficult to grow single crystals of boron arsenide. The reason is the following. Boron has a very high melting point, over 2000 degrees C. Chemically very also stable. On the other hand, arsenic does not have a melting point. It does not melt. Instead, it goes from solid to gas at 615 degrees C. Very toxic and also very volatile. So just think about it. You have a solid, very high melting point. You have another material which is vapor at above 600 degrees C. And how are you going to make them to grow single crystal? It's tough. But of course, you can start to think of use diboron or arsine, use both chemicals, let them decompose and then form boron arsenide. But the issue is, as you know, a lot of people in semiconductors, arsenic, diboron, arsine, extremely dangerous. If you have 1 ppm, 1 part per million concentration in air, and that kills you. So we do not wanted to get into those kind of nasty gases. And then we started to look at the solid. And then on top of all those issues, another issue is boron arsenide itself. We look at the phase diagram. It decomposes at about 920 degrees C. So chemically, it's not stable above that temperature. With that, basically tells us if you want to grow single crystals, you have to maintain the temperature below 920. Otherwise, it's not possible. So with that, and then we move on to slide 11. Our first try is sort of successful, but not really a big success. And we made some crystals use a chemical vapor deposition way or chemical vapor transport way, in fact, to be precise. We use some iodine to react with boron, we add a reactor with arsenic, and those vapors transport from the hot side to a colder place, and that has to be below 920 degrees C. And we made some crystals, and as you can see here in the picture. And then we measured in collaboration with Chen's group at MIT. We measured thermal conductivity about 200 watts per meter per Kelvin, which is definitely not as high as predicted over 2000, but it's a good start. And the reason for that low thermal conductivity obviously is the crystal quality is low. As you can see from this picture, in the picture A, you can see it's not really single crystal. A lot of it's like 2 domains, really. And then we kept improving the growth process. One thing is when we look at the move to slide 12, please. When you have multiple domains inside a crystal, that means there are 2 or 3 multiple nucleation happens. So how to eliminate the multiple nucleates, and so that only a single nucleation site is happening, and that's the way we start to do it. So we were using either as grown boron arsenide as a seed, or we use other seeds like quartz fibers, and also other fibers we have been using. And move on to next slide 13. Use by controlling the nucleation number of nucleation sites, we were able to get single piece crystals. Like in the picture C, you can see it already. That's a definitely from a single nucleation site you get a crystal. So then we were able to measure thermal conductivities, close to somewhere 350. In that range, it's almost double the previous number, but still not as high as the 2000 predicted. Well, research is never easy, and also it's never going to be that quick. So we continued the improvement. Let's move to slide 14. And back to, we started in 2013. By the time like 2017, 2016, 2017, we were able to make crystals much bigger, and it looks like much better. In this picture, you can see a few millimeters length or dimension, and they are indeed single crystals in the X-ray diffraction pattern. You can see this because it's cubic structure. Very often the surface is a 111 surface. You can see only the 111, 222, or other 333 surface are detected here by the X-ray diffraction. Move on, please, to the slide 15. So with those kind of larger crystals, we were able to measure the transport properties. So what we did is here we use the silicon at the lower picture. We have a silicon as a standard reference sample, and then thermally connected with our boron arsenide. And then we have a heater, we have a heat sink. We basically build a thermal gradient. So because we put this whole thing inside a vacuum chamber with whatever the heat pass through the silicon, it has to pass through the boron arsenide. But of course, there is some heat leakage through the measurement wires. On both silicon and boron arsenide, we have two pairs of thermocouples, measure the temperature so that we know the temperature gradient, and also we measure the transport, thermal transport in that way. So based on the equation, obviously, we know everything about the silicon, and then we should be able to calculate what's the transport properties of the boron arsenide. As you can see at the beginning, we were not able to get very high thermal conductivity because this is a macro scale, notch scale measurement. And let's move on to next slide, slide 16. So on this slide, I'm showing you the multiple methods measure thermal conductivity, like the TDTR, FDTR, Raman, also transport. So basically, the crystals at that time, we grow some crystals. Multiple methods measure the thermal conductivity around 1,000. The highest could be somewhere 1,200, close to 1,300. And the lowest, low could be very low, a few hundred. Okay. So that is the first demonstration. Boron arsenide indeed can have very high thermal conductivity. But why is not close to 2,000 as predicted yet? As you can see here, later on, theoretical prediction found the original prediction over 2,000 because without consider the 4 photon scattering effect. Later, when they add the 4 photon into the picture, and they found the theoretical thermal conductivity should be somewhere probably 1,400. So now the experimental data sort of proved it's very close. But one thing I want to point out here is I never believed this material will have this limit by this theory, because the current crystal we have, it's highly, highly defective. With this highly defective crystals, if we already get the thermal conductivity close to theoretical prediction, I think then the theoretical prediction is not accurate, because as soon as we get rid of all the defects, I have the full hope the thermal conductivity will be over 2000. That's, let's say, when it's not a matter of whether or that will happen. To me, it's just a matter of when that will happen. So I fully believe in that. Let's move on to slide 17. After that report back in 2018, and we continued to improve the crystal growth. So in the lower left picture, so here I'm showing you if I have a quartz fiber, and if the fiber act as a nucleation site, the crystals normally nucleate on the fiber. When it grows radially to the quartz tube, to the wall. And the quartz tube is only about 6 millimeters in diameter. That means your crystals will be limited not more than 6 millimeters. And what if we can reposition the quartz fiber instead of horizontally, but if vertically? So if you look at it, because in fact I have a animation, but since this platform cannot show the animation, so I can only show you the picture. Please move to slide 18. So when the top left picture, the orange bar at the right end of the quartz tube, and then I put the bar vertically, and now if the crystal grow out of the quartz bar and along the quartz tube direction, and then I should be able to grow crystals larger than 6 millimeters. Indeed. So here is a picture I'm showing you in the middle, top row middle. It's a 7 millimeter crystal grown, and if you look at the right of it, it's the quartz tube, and the crystal grow from left to right, and then when it heated the quartz inside the wall, and then the top part continued to grow, the bottom part stopped. And that's very vivid, showing the nucleation and the growth. On the lower right picture, I'm showing you taking out from the quartz tube. This bar is the quartz bar, and the crystals grow on top of the quartz bar, and multiple crystals grow different directions. And those crystals have shown thermal conductivity measured in the table above 1200 watts per meter per Kelvin. We also tried other nucleation sites like gallium arsenide, silicon, sapphire, and turns out the gallium arsenide is similar to quartz tube, yield high thermal conductivity. But the silicon and also sapphire give us much lower thermal conductivity due to contamination from either aluminum, oxygen, or silicon. So on the right column, we showed the transport measurement is a mobility is a few hundred. Again, that's because the non-uniformity of the sample. So if you look at to slide, or move on to slide 19, that further shows the larger scale, shows the crystal size, and whatever I showed in the previous slide. Okay, I'm not going to repeat that. Thermal conductivity is very much related to isotope effect. As I pointed out in earlier, diamond, it's carbon. Carbon has carbon like 11, carbon 12. I think carbon also even has carbon 13. I'm not 100% sure. And if you have isotope pure, you get over 3000 thermal conductivity. So what about boron arsenide? So how the isotope were affected the thermal conductivity? From the simple physics, from the simple physics point of view, the isotope effect should not be strong, because whatever boron 10 versus boron 11, the mass difference there is a small fraction of the whole chemical weight, because you have arsenic. Arsenic has the atomic mass much larger than boron. But still, we would like to test this hypothesis. So, which is why we grow boron isotope pure single crystals here, and then we tested the thermal conductivity at the lower left table. As you can see, pure boron 11 and pure boron 10 both have thermal conductivity about 1200, which is very similar to the natural boron, also 1200. So this is a great advantage for future applications, because if you can use natural boron, and your cost would be much lower than the isotope pure. This is very important. Okay, let's move on slide 21. So on this slide, I'm showing you another. This is a summary, basically. Recently, also as recent as last year, Gang's group, we together proved that cubic boron nitride. By the way, cubic boron nitride does not have bigger crystals. They were made by diamond anvil cell. It's only some micron size, high temperature, high pressure, just like a diamond is made. And then also they made the isotope carbon 10 and then isotope carbon 11 boron nitride, and also natural boron nitride carbon. So now you can see the isotope pure has thermal conductivity over 1500, but the natural boron nitride, cubic boron nitride, it's less than 1000. Not like the lower panel, boron arsenide has basically insensitive to the isotope concentration. Again, as I said, this is very important. Not only the synthesis method, boron arsenide, you can make large size, but also the property is very unique. And then move on to slide 22. Very often, diamond and other materials, their coefficient of thermal expansion property is also not ideal, not matched well with other semiconductors. Here, I'm showing you on the right panel, you can see there are different kinds of semiconductors, like gallium arsenide, aluminum arsenide, silicon, and others, diamond boron, cubic boron nitride. They are either very small, CTE, or very large, like gallium arsenide. Not like boron arsenide. Boron arsenide has CTE around 4 times 10 to minus 6 per Kelvin, which is very close to like silicon and with other materials. This is also a big plus for future electronics manufacturing and also lifetime thing. And if you move on to next slides. So when we were studying the crystals, we found sometimes we get band gap measurement is different from the theoretical calculation. The theory calculated says that the band gap should be 2.1 EV, but very often our measurement is anywhere from 1.8 to 2.1. It's not consistent, multiple band gaps. So we did in collaboration with Professor Shi at UT Austin. We took a boron arsenide crystal, and they measured the band gap from the edge, surface to surface. So basically across the cross section. And what they found is close to the surface, the band gap is about 1.9 EV, and in the middle, it's about 2.1 EV. What does this say? Well, this to me immediately tells me our crystal on the surface, there are defects. And inside, probably there are much pure, and also should give us higher thermal conductivity. But up to now, our thermal conductivity measurement all are on surface. So this is why earlier I was saying it's not a matter of whether it will happen or not. It's a matter of time when it will happen. Thermal conductivity will be higher than 2000. And I have all the confidence that will happen. And because the quantity, okay. And so we have been move on to slide 24. We have been improving the crystal step by step. This is a tedious, it's a time-consuming thing, the growth-wise. As you can see here, some crystals in the middle, pretty uniform. Size-wise, a few millimeters, and we have been, trying to improve the crystal. Move on to next slide, slide 25. And we have also, as you can see, the TDTR measurement is very time consuming. You have to deposit a induction layer and then to do the TDTR measurement. And we were thinking, is there any way we can quickly screen the thermal conductivity? And we found that indeed we could use the so-called time domain or time dependent thermal photoluminescence method. And so basically, if you shine laser light to the surface of a crystal, if the thermal conductivity wherever, because anywhere they absorb the energy, the temperature will rise. If the thermal conductivity is very high, and then the temperature will rise to a very limited number. And if the thermal conductivity is very low, and the temperature will rise more. So here I'm showing you in panel D, and the two samples with the blue and red, thermal conductivity is only 200 something, and the temperature rise is lower than the other thermal conductivity is 160 watts per meter per Kelvin. So basically with that, and then we can quickly scan or screening the crystal quantity. And the next slide, 26, showing you we were doing the scanning. We found on a crystal on both sides, they are different. And even on the same side, the uniformity is also not that good. In like P2, we have lower thermal conductivity, about 400. P1, we have thermal conductivity close to 700. And in the other region, lower color, red color, thermal conductivity is over 1100. So that means, again, the crystal is not uniform. But we do have this way quickly screen the quantity of crystal, which also can feed back to our growth effort, try to change the growth parameters. And move on to slide 27. I'm going to be done very soon, okay? Slide 27, as you can see, with better and better crystals back in 2019, we were able to only measure the band gap about 1.8 eV. By 2020, we will be able to measure band gap, some good crystals already close to the theoretical 2.1 eV. Okay, so move on to the next slide, 28. This is the most recent report in Science about the high mobility. We use a pump and probe method, and basically you inject energy by laser beam, and you pump the electrons from the valence band to the conduction band, and then they will diffuse, they will move. And based on how fast they move, and then we can calculate the mobility. So here we cannot differentiate the electrons from the holes because they move basically together. And also in this material, both the mobility of both the electrons and the holes are high. The predicted value of electrons is 1400, and the holes are 2100. And so by measuring, by also simulation, we found indeed we have ambipolar mobility 1500. That's basically very close to the theoretical prediction. The ambipolar should be 1660. So our measurement is 1550. This is a collaboration between my group and Professor Jimmy Bao's group here at the University of Houston, and also Professor Liu Xinfeng's group in China. The reason for that is because the first author, as you can see here in the paper, Shuai Yue, was a postdoc in Professor Bao's group. After he finished his work here in University of Houston, he brought some sample back to China and then used some more advanced method there, and then found this high mobility. At the same time, if you move on to slide 29, Gang Chen's group, in fact, predicted the high mobility, carrier mobility in 2018 and published a paper, theoretical paper then. But ever since, we have been collaborating, trying to measure the high mobility. And then by last year, in fact, close to end of last year and earlier this year, and indeed, we were able to confirm the high mobility. Not only high mobility, and his measurement is also he can measure the same spot of the carrier mobility and also the thermal conductivity. If you look at the lower row of the two panels in panel A, as you can see here, it shows that the thermal conductivity is over 1,000, and also at the same time the carrier mobility is over 1,500. That's in fact the first time have the same spot measured both high thermal conductivity and high carrier mobility. This is absolutely important and for a semiconductor. So now let me summarize. Oh no, I still have a couple more slides. Not too many more, just a couple. So at the same time, as I said, we here at the University of Houston, we have been trying to measure the transport by Hall effect. And here I'm showing you the sample, how the sample is mounted. And they transport across a longer distance, normally at least 2 millimeters, not like the optical way by either Gang Chen's group or Jimmy Bao's group use optical way. Optical way only measure local region, a few or less than 100 square microns. But the transport measures uniformity of the sample. But we were not able to measure that high, like above 1,000. The highest we measured so far is about 700. Okay, move to so with that, I basically let me summarize what I talked about the boron arsenide. So normally a semiconductor, as you know, either silicon or gallium arsenide or other materials. There's no semiconductor has high thermal conductivity, has high mobility, has also wider band gap, and also has very friendly or matching CTE. But boron arsenide has all properties together. So this is unbelievable. This is why we are going to continuously pursue this material. And I believe this material will be better than silicon, probably. I'm not saying, near term, 5 years, you are going to use boron arsenide everywhere. No, that's not what I'm telling you. What I'm saying is this material is very promising. We did a lot of more efforts, not only research efforts, but a lot of people, financial support, and to really get this material grown in much larger size, much higher, much more uniform, with much higher quality, and to show even higher thermal conductivity. I have the belief the thermal conductivity will be above diamond, higher than diamond. Mobility will be, because both electron and holes are about the same, and it will be much higher than silicon, and it's even higher than the gallium arsenide, probably somewhere 3,000 range, or even hopefully 5,000. I don't know, but definitely it will be higher than the current 1,500. So I'm very hopeful, and I will stop here. If you have any questions, I would be more than happy to discuss and then try my best to answer your question. Thank you.
Great. Thank you, Dr. Ren. Quick question. Eli, you there?
Yeah.
How long, dude? I just noticed you got in, man. It's good to see you, brother. Haven't seen you in a while, man. Um, how long you been in the room for?
I just joined like at slide 20 or so. Pretty not very long.
Not very long, okay. But you got a gist of what's going on, right?
Yeah. So I mean, my question
Wait,
was. Oh, go.
this is what I'm saying.
Sorry,
This is
go
what I'm
ahead.
saying. So, like, so Dr. Ren, Eli is one of my favorite people on Clubhouse, as well as a lot of others, right? So it'd be just nice for the rest of us now. This is a good time to go get your popcorn, stick it inside of your microwave, and we'll have Eli and Dr. Ren just converse together. I just want to hear you two talk, man. This is gonna be interesting. Go ahead. Like, not just one question, but like have an interaction, bro.
Yeah, sure.
Well. So thank you. I'm kind of distracted right now, so I don't know how deeply I can engage. But one thing that came to mind is and I hope I didn't miss this if you addressed it. What do you see as the potential for photovoltaic applications as part of multi-junction photovoltaics, or just by itself tuned to specific the corresponding optical wave band?
That's a very good question. For photovoltaic, as you know, since you're asking this question, I would think you are definitely expert in photovoltaic. I had some experience, some research on photovoltaic. Right now, the most used photovoltaic material is silicon. As you know, silicon has issue. One thing is the band gap. Silicon band gap is only 1.1 eV. Now, with 1.1 eV, solar spectra has the UV, ultra UV part that will generate so-called hot electrons. And the silicon, when temperature goes up and the band gap further decreases, then that's why the hot electron is not good to the silicon. Now use the boron arsenide, the band gap is 2.1 eV. If this one is, put together, use a multi-junction with silicon, and then it will be much more beneficial to convert the high energy part of the solar spectrum. Sort of, gallium arsenide, you can dope different kind of gallium arsenide. You have triple junction, you get efficiency over like 40%. So with boron arsenide and itself, we don't know itself how high the efficiency it would be, because even though you take care of the hot electron part, but you lose the non-wavelength part. I did not do a calculation, but I would think just the boron arsenide alone probably will be close to silicon, or if not better, will be close. And then if you add silicon together as a double junction, and you have a hope probably get to gallium arsenide, which will be much cheaper than gallium arsenide.
Yeah, that would have been my guess, so I'm glad to hear that's your intuition. The other thing that I think is potentially attractive here is the combination of high electron and hole mobilities. My guess is, and maybe you could correct me if I'm wrong, that would reduce the loss of efficiency due to charge carrier recombination.
Of course, that's absolutely right. You are there. You're right on spot. With this high carrier concentration, carrier mobility, and you can relax the thickness a little bit, so that you can have much higher absorption than silicon, much lower recombination rate. In fact, our data shows that the carriers of boron arsenide, excited carriers, have much longer lifetime than silicon. So that means all the excited carriers will be harvested instead of recombined. So in that sense, and then the efficiency should be higher.
Yeah, I hope it turns out that way, because this does seem quite promising. Yeah. So I've done some and this is, you know, just really preliminary calculations on density functional calculations of mechanosynthesis, positional mechanosynthesis, where you're using molecular tools to manipulate things and building things up atom by atom, molecule by molecule. Not of, obviously, of boron arsenide. I have done some with boron nitride, and for the cubic phase, I'm not confident that it'll work out, at least by the strategy that I've chosen, though there are still more strategies to evaluate. But I'm going to, you know, at some point, and this will probably be months before I have the time, try similar things with boron arsenide, and you know, maybe we can be in touch about that. It's hard to extrapolate from what I've seen so far with boron nitride, because boron at a surface, it really wants to grab anything that gets close, and I kind of expect that it would be even worse with arsenide, just because that's lower electronegativity than nitrogen. But it's a challenge that I'm looking forward to poking at.
Well, for that aspect, I have not looked into that in detail. But one thing I want to point out is, you know, boron nitride, cubic boron nitride, or diamond, all those things are very wide band gap, much wider than this. So definitely, sort of, we call it insulator, right? It may not be useful at all for photovoltaic application, but of course, if you're not talking about photovoltaic, that's okay. Another thing I want to point out is boron arsenide. It's very very chemical resistant. What we are doing is, when we grow the crystals in a quartz ample, and when we take it out, how do we take the crystal out? We drop everything into aqua regia. As you know, aqua regia is so reactive, even react with gold, right? But boron arsenide survives. So that's how we clean boron arsenide. And in this way, it has another, I didn't talk about this during my presentation, it has another feature which is not too many materials has.
That's pretty remarkable.
Yeah.
Yeah. So yeah, it's the boron nitride stuff is not for electronic properties, at least not you know, in the modal case. It's for structural and high temperature and chemical resistance.
Exactly.
That I've been interested in.
Yeah, it's not so much as a functional materials, boron nitride, cubic boron nitride, and diamond. It's more like structural materials. But the boron arsenide, it is really a semiconductor. It's a functional materials. And as you can see, in this world, we do need the structural materials and also functional materials. But you know, structural materials, we do have a lot of them, very good. But it's, for the functional materials, so far, electronic silicon is the most popular. But what's next step? You know, next material for high power electronics? Really, boron arsenide probably will be the future for that.
Well, certainly, it's a good contender. I mean, the high mobility for both holes and electrons is unique and promising.
Yeah, and also the high thermal conductivity.
Well, thank you, and perhaps I will be in touch with you in future months if I take on the mechanosynthesis positional nanomechanosynthesis of boron arsenide.
Sure. Anytime if you need anything, you can send me email. Yeah.
Great, thanks.
All right, so like at this point in the convo, how about we try to, because we got like a lot of scientists in here, but we also got a technologist that can get deep into conversation, and then we've also got folks that can't get so deep into into the technical side, but maybe we can talk about, let's talk about applications, right? Especially with like Eli here or others in the room, right? It'd be nice, based on Dr. Ren's presentation here. Let's kind of throw this out to the room. What are some applications, or what are some things that will change with this technology as you guys see it, based on his presentation? Maybe we'll have Eli. You can maybe head that up. But what are some applications you see? Some ideas you might have for Dr. Ren here. Go ahead, and then others can chime in.
Well, I mean, the first was photovoltaics, and we already discussed that. And I would imagine that high electron mobility transistors would be pretty high on the list. And again, for like power applications, as was mentioned, I haven't really thought about it in enough depth to go much beyond that. So I'll just pass that to anybody else who can say anything more intelligent than me.
So definitely, fast electronics, high power electronics will be the immediate consideration.
Yeah, so I read an article that came out in the news that Intel, I think somebody in Intel said that with the current computing power, we cannot achieve all the plans we have, like the metaverse and having all the data on blockchains, and that it's kind of unrealistic. So would your technology basically be able to address that? And then also would it also address the semiconductor shortages that we currently have? Like, how far along is it also to like to use it? Like, did you get some money from our current president to put that into work for the current sort, and to develop this here in the US, to manufacture it here in the US?
Well, this is a very early stage. In the very early stage of the research, it's very promising with all sorts of properties we talked about. Fast electronics, high power electronics, heat dissipation. When you talk about high power electronics, there's always heat generated. In the past, if it's silicon based or other semiconductor based, and you have to find a way to dissipate the heat. But for this material, because its own thermal conductivity is so high, you may not have that issue. At the same time, due to the fast high carrier mobility, your heat generation also be due to the very high band gap, large band gap. The heat generation itself will be, I think, will be smaller, much smaller. And even if it does generate the heat, and then you have the high thermal conductivity, it will dissipate very quickly. And for the semiconductor shortage wise, this is not immediate material ready for use yet, and it still require a lot of more research, a lot of more funding for to make it, or to prove whether it's going to be able to realize all the promises. And as far as the funding, honestly, tell you the truth, we used to have federal government funding. This program, in fact, I started it with my own funding, other funding sources, and later on we got funding from the U.S. Navy Office of Naval Research, and that program has run out. Right now, I don't have any funding on this project. I'm just doing this research myself, use my other sources, low federal government funding.
Oh wow, that's That's quite sad that you that you don't get funding for this. Funding should be all over you to to get this. The, so is this also going to, what's about the size? Would I know this would be good for temperature control, and what about the size and the weight? Would it be better for like small drones and applications like that?
The size wise, they of course depends on your device. The density of this material is not that high. As you can see, boron is night, right? You are thinking the boron arsenic is a 1:1 ratio here. Boron is lighter than silicon, and arsenic is heavier than silicon. But at the end, I think I don't have the density number in front of me. I think the density probably similar to silicon. So for any like application mass, if it's a concern, probably it will not be too big a problem because it's not too much heavier than silicon.
Yeah, thank you. Does anyone else have questions?
I have a question.
Yeah.
Can I ask you a
Yeah.
question? Thank you, Dr. Shan, for the wonderful presentation. And yeah, by me, my background is a PhD in microelectronics, and I work on self-powered sensors, mostly for IoT applications. And also, we work on energy harvesting, like photovoltaics or thermoelectrics, etc. So my question is it like how is it like you are talking about the band gap? Is it direct band gap, or I think it's you're talking about the indirect band gap,
It
right?
is. It is the
Of
indirect band
1.6.
gap at 2.1 eV. The direct band gap is 4 eV.
Okay, thank you. And one question already Ellie has asked about the application for photovoltaics, and along with it, I see it's also a good thermoelectric material. It could have. Yeah. So my question is, the silicon is widely used in the industry because of the compatibility with MEMS or with the the ASIC can be more easily integrated. So my question is, how compatible is it with the industrial process right now? Because can it be as robust as silicon, or yeah, that's my second question.
So
Thank you.
yeah, the about the compatibility, there are a lot of compatibility factors. Structurally, mechanical property wise, physical property wise, all sorts of those things. All I can tell you is so far as far as I know is the material itself is mechanically stronger than silicon. We did the hardness measurement. It's definitely much stronger than silicon, and also it's more chemically resistant. As I said, we boron arsenide survives in aqua regia, which that will melt gold, dissolve gold, in fact. And then the thermal coefficient of thermal expansion matched very well with the other semiconductors. And at the same time, the fabrication at this time, because we have not, what we know is it can be made in large size. And after it's made, and then I would think should be able to be compatible. Then you can do a lot of processing on top of that, either 2 terminals, 3 terminals, whatever the devices you are going to process. So I just expect probably not too big a problem, but I don't know the detail before somebody really take it and then give it a try. So that's my current thinking.
Just a sub question regarding the arsenic. Do you think it's toxic and it can be as successful as silicon in the long run?
So the arsenic itself, when it's in vapor, of course, it's toxic. But when arsenic formed a compound with boron, the compound itself is fairly stable. We have been annealing the sample, the material boron arsenide, at anywhere 500-600 degrees C. There's no vaporization of arsenic at all. So I don't think there is a problem.
Thank you very much.
Mm-hmm.
I have a question also. You basically talked about the, temperature control. How does it behave in water or at a low temperature, if that makes sense?
So yeah, as I said, this material is very stable and also very chemically resistant to a lot of chemicals, and obviously water, it's not going to destroy it or degrade it. That is the current understanding. So temperature and water, temperature as I can say right now, as long as it's lower than 700 degrees C, shouldn't it be a problem. Water is not a problem at all.
Awesome. Thank you.
Yeah.
Yeah, hi, Dr. Ren. Quick question. Since this is electron driven, we see that electrons behaves pretty differently when it comes to with crystalism, other atoms. Do you know any research, or do you know anything about the conductivity when it comes to the position of electron going into the nucleus and whatnot, when it comes to basically energy? Yeah, thank you.
I'm not sure I fully got your question. Are you asking about the electronic conductivity?
Yeah, in general.
Oh, in
basically.
general, okay.
Yeah,
So far, we have done some preliminary measurement, and the carrier concentration is still very high. Normally, it ranges in 10 to 18th to 10 to 20th power, which is why we have not gone to the intrinsic state, which is why also as made crystals is always p-type at this moment, and the conductivity is somewhere in the range of maybe 10 to -2 power to 10 to +2 power, in that range, basically 0.01 to like a couple hundred siemens per meter. And we have a idea why it is always p-type, and so far we have not got any crystals showing n-type yet, but I think we know why, and we are going to next try to do some controlled experiment to make it into n-type. As you understand, that any semiconductors, you have to have p-type and n-type. Just one type is not enough. So that's kind of preliminary measurement we have on the conductivity wise. And obviously, you have the photo induced conductivity. You shine light, and then like any typical semiconductors, you excited the electrons from the valence band to the conduction band, and then you get a much higher electrical conductivity.
Thank you. Thank you.
Yeah, does anyone else have a question for Dr. Ren?
Yeah, you can send my email to all the audience, and if they have questions after this, they can always send emails to me.
Dr. Ren, I had a very quick question. That was a great
Mhm.
presentation. I was curious how long it might take to scale this technique to commercial applications. Like, what would it take for this to become standard technology rather than just experimental technology?
That's a great question. That, as you understand this very well, you know this better than me. Any technology from the lab to the market, there are two important factors determines it, as I can say this. Number one is the demand, market demand. If there is a strong market demand, and then people will try to make it. And then, of course, number two is you have to have a lot of money and to do it. So at this moment, as I said earlier, I don't have any government funding. So the research in my lab is going on. I can tell you, in fact, in the whole world, this kind of crystals, no other lab has better crystals, as far as I know, than us. First of all, it's not too many labs are doing this research in the world. Secondly, we still have the best crystal. We know what's going on the crystal growth side. And without the government funding, and then we are making progress, very good progress, but not fast enough. Obviously, in order to make this NAP technology to application, we still need a lot of people to work on it, and also not funding to fund the people to do it. So I really can't say how long it will take. Depends on how much funding the private industry will put in.
Sure, I understand. Thank you for the
Mhm.
answer.
Have you thought about submitting for a SBIR grant or a STTR grant?
Well, let me ask some of you a question. How many of you know Professor Gang Chen at MIT? Well, the reason I'm asking that is if you know a little bit about Professor Gang Chen, and he was arrested by FBI very incorrectly by mistake after 1 year harassment, and this year all the indictment, all the charges were dropped. But that destroyed his career. And now anybody, if you are not, you know, originally born in this country, or you are not white, we are very careful taking the government funding, because any government funding will put us in a big risk. Which for that I am reluctant or hesitant to write any proposal right now.
Yeah, I totally understand. Since they changed, when was it when they changed the rulings that you cannot have any collaborations with foreigners or people that are, moving back to their home country? A friend of mine, she did her PhD project and then went back home to Portugal to finish up writing and analyzing the data to then finish the dissertation. And she got in trouble for the fact that she was analyzing the data in a foreign country. It's crazy because all the research, almost all the research in the US is done by foreigners. We are all immigrants. Look in the lab, go into any lab, almost everyone is an immigrant working on very low wages. And we were almost all educated by our home countries. So it's free resources the US is taking in from other countries because they didn't even have to invest in us to do this work, right? All the education was done for me in Europe, and paid by Europe, Germany and Portugal, and in almost everyone I know, and then they harvest all the highly educated people around the world. We do research here, and then we cannot even collaborate with our home countries. That's, I'm sorry, but that's just exploration. And the wages are exploration. That's why nobody, like almost no Americans, are in research at universities, because the pay is so low. You couldn't even pay off your student loans with the research job. So I'm sorry, my rant, but yeah.
Yeah, I asked that question because I actually submitted to the National Science Foundation, and they read over the proposal, moved me to a brand new solicitation that was created off of my submission, and then asked me to resubmit. So that just seemed very awkward and very weird. You know, if you had enough information that I provided in my submission to create a brand new solicitation, that means that you shouldn't ask any more questions. If you get what I'm saying.
Oh yeah, that's another whole problem, that some people get, read the grants and they have a bigger name and just take the grants and
So
and do it.
sorry about that, Katarina, but I'm pretty sure like all of the people or most of the people in this room are quite intelligent and intelligent enough to know why this is actually happening. And I haven't heard anyone bring it up. So if you were to actually look at the trends around the world since the pandemic, we've been heading towards a Cold War-esque kind of environment around the globe. And you would just have to look at the Taiwan Strait right now to see that actually take effect. I shared just an article from the FBI. There's a lot of counterintelligence and espionage going on in the world today. So, actually paying attention to the actual state of the world rather than just being immersed in a science textbook would bring one to realize why it is so shrouded in controversy. And just looking at the semiconductor issue alone, one can look at that. There were Confucius institutes that were shut down as a result of this as well at several universities. So it shouldn't surprise anybody that this is happening.
Yeah, it's the same issue over and over. I mean, ultimately, what's it actually creates a great opportunity too, right? Where you just need to create a place where the techies and the scientists and innovators can come and play together, like a little playground, somewhere away from all the mess. You got a lab, you got a maker space, you got your 3D printers and CNC machines and all your lab equipment you need, and then we just go there and show up and guard the gates. That's it. Like create a little gated, yeah, your own gated community, right? Of like scientists and engineers, and you publish things. The solution that I see it as is you just get a bunch of people. Then you have to create a sustainable solution. I've thought about it quite a bit now, and it's get the brains in there, work on creating licensable tech. That's it. Just one focus. You just create stuff, give a license to it, license it out, someone else scales it, and that's kind of the insulating factor. And then you just kind of grow the community and get more equipment and more people in there to kind of just do their own research, be autonomous, do their thing, and as groups, and just punch out stuff that's licensable that goes out and then comes back into the group as a whole and gets split, into the group that originated it plus the other groups working. So everybody kind of works like it's socialism doesn't work at scale. I don't think. I'm pretty sure it doesn't. But in a tiny space, in a small environment with like-minded people, a set of rules around that would, I think would work. So Yeah, I mean, it's sad to hear, like, you know, I mean, me personally too. I mean, I experienced, I was like, I don't want to take, like, there's a lot of funding you don't want to take, right? It's like, no, I don't want to take that funding. I don't want to take that funding. We don't want to take this investor funding. We don't want to be controlled by these people. Or, okay, they take this government funding and you can't even do anything with the work you've done for the last, what, 20 years or something? Like, how long have you been working on this, Dr. Ren? And, you know, how many years?
This particular project is about 10 years.
So 10 years. So basically, if you took the wrong funding, then 10 years of your life just, you can't even control what you do with 10 years of your life and your research, right?
Well, in fact, whatever happened in the past. What we are afraid most is, you know, things happening to Gang Chen could happen to anybody, and that's why we are afraid. You know, someday they may arrest me for since they say I did it incorrectly, but I didn't do anything wrong. At the end, just like Gang Chen, they harassed him for a whole year and dropped every accusation, and then even they didn't say sorry. You know, this kind of thing is scary.
Yeah, for sure, man. It's sad,
It's
right?
very sad.
It's getting and it's like that for everybody. And then, you know, like, what do? They put, and then they also put the pressures of putting people under R&D contracts and non-competition and non-disclosures and all this stuff. And by the time you're done, you're walking around as a scientist. You're a scientist that's supposed to have a free mind and blue sky to innovate and, you know, find solutions to problems. You can't talk to people outside of here. You can't talk to those people. You can't tell anybody about this research. You can't do this. You know, you should just basically be quiet, work in this little silo, and be panicked a lot of times, right? You know, whether you're saying the right things or wrong things. I mean, isn't it's kind of sad how our scientific community, especially in corporate America, right? Like they're under R, like they can't say anything. If you're in an R&D department inside of corporate, you can't say shit, right? You might as well just like disconnect from the rest of the world when it comes to your specific stuff. You know, it's just I've seen this over and over and over and over again. So many of my friends, and they're very, very smart, working in high level R&D roles, because that's where they end up at. You know, the technologists that are really smart, you know, are either leading other technologists or they're innovating with other technologists, and they're all handcuffed and silenced from collaborating together.
Yeah. So
I think it's almost done like that on purpose, man. You know, and it's like it's frustrating, like you said, because you know, just understanding the basic principles of science, we know that there's infinity concepts, you know, like, so even if somebody applies for a patent, you know, being as intelligent as we all are, we can look at that patent and figure out ways of doing the same thing with a different type of material potentially. So it's like, what is the real point sometimes? You know what I mean? I think it's really to keep the less intelligent from reaching intelligence almost. You know what I
yeah.
mean?
So
No, hold on, let me clarify. It's less worse than that.
just so
It's
people
so
are
that
aware, quick.
it's so that the less intelligent find ways to control the more intelligent, right? Because that's what it is. It's like, look, man, I'm an entrepreneur, all right. I'm a technologist entrepreneur. You guys in here are a whole lot smarter than me when it comes to the science and technology stuff, right? And so, you know, most guys in my position would look at that as a threat and be like, we got to control these people, right? Under contracts. Well, they might be really smart at that, but we're smart at business, right? And people stuff and control. So we need to control these people because we can't like replicate. There's only a few of these people, so we got to like, what the hell? This is a stupid way of thinking. Why don't you say, hey, just take care and support these people and create an environment where they're super happy and, you know, share in the wins, and let them collaborate with, like, support them and attract more of them by doing that, rather than like trying to enslave them. But then again, I mean, we had slavery forever in human history, right? This whole concept of humans enslaving others. So the only way scientists are going to be free, in my opinion, is scientists get together to create a free, the scientists and engineers and technologists, they have to kind of get in and create a collective, you know, like, and that's what I think we're all trying to do. We've been talking about that, like me and Eli and Katerina and Lisa and like other folks on here and Kyle, like everybody wants to make that happen, Doctor, you know. So
so
you know,
will you
We're gonna try to figure
We
that
Yeah,
out.
absolutely. And doctor, I just want to say quickly that like I really appreciate and enjoy that you're here with your time and energy. And so even though I brought up like the reality of the situation, it doesn't at all mean that I don't have any empathy at all for your friend that was in that terrible situation. It's just time that people wake up and realize the times that they're living in, and we can't just get around together and sing kumbaya. This isn't reality. The reality of this situation is that if anyone's interested in technology and science, look at what happened to technology and science during the Cold War, and then kind of like look at that and then look at today's situation and then wonder, okay, is this time for let's get around the campfire and sing kumbaya, or is this time to wake people up to the reality of the situation? Because I was actually removed from a room just sharing information about the genetic data and the difference between these countries and their opinions and their ideologies is directly contributing to genetic data and genetic research. And, you know, there's certain countries that they don't care about the rights and freedoms of their people, so they'll just that do care about the rights and freedoms and are wondering, well, how far behind are we going to get if we just allow these regimes that don't care about the rights and freedoms of their population to take all of genetic data to work with that? How are we going to keep up scientifically when they have so many data banks and freely accessible, whereas people in countries with rights and freedoms seem to want to protect their genetic data. So this is just a situation that's going on today, and it would be good for people to do some research and instead of being attached to their ideologies, look at the reality of the situation and what's going on and the cause and effect relationship of that. And I'm done talking.
I recommend quickly the proof by Andrzej Bauer, The Countable Reals. I think it helps grasp knowledge in situations where of information overload. Kenny, I sent it to you. It's in the chat. Dr. Ren, I'll send it to you as well. But I'm at the soccer field, so I have to just listen now.
Thank you guys so much. In fact, when you are saying that the slave and the slavery, I I I want to tell you my feeling. Okay, as a scientist, we always feel we are slaves. You know, we work so hard, we get technology, get science worked out, get technology ready for the society. And then the government, different branches, and then they could do whatever the bad things to us. So that scares us. Just like the slaves, you know, the slaves, they go to the land, they prepare, grow the food, they cook the food, take to the table, and then they don't have a right to eat the food. And then the landlord, they eat it first, and if they don't have anything left, if they are nice, they give it to the slave, and if they are not nice, the slave has to be hungry. So I fear that we as scientists just the same like the slaves, and the politicians are so bad, and they just mess things around, doing the bad things, and then do everything for their own benefit, not really think about the people and the country and the world, which is very sad. That's what's going on.
I want to add one point, like all over the world, like the scientists are taken for granted and just seen as a pushover. I mean, really, like the voice is not heard anywhere in decision making or even the. I mean, I don't know. We all talk about taxpayers' money, and even taxpayer don't really care where the research is being funded or what is the priority of funding. So it's like it's pathetic, and I really appreciate when you come up. I mean, you are such a acclaimed researcher, and you come up with this reality, and I really appreciate it.
Thank you.
Yeah, Dr. Ren, we should go grab lunch together sometime, man.
Sure.
Down the street from
Yeah.
you here in Houston. Yeah.
So I can tell you one fact is about, let's say, about 6-7 years ago, when we wrote proposals, our proposal success rate is at least 50%. We do, because we do very good science. Up to this moment, my group has published with my name, published like 600 papers, and I have more than probably about 100 of those papers out of 600 are highly cited in the world. So-called highly cited is top 1%. And in the past, I didn't have any problem to get the funding. But during last 6-7 years, I have basically zero funding. And whatever I write, and they just shut it down. I don't know what's going on. Is it? It's not because my productivity is going down. In fact, my productivity is going way up than 6 years ago, and my impact of research is also going way up. I just don't understand what those people are doing, and then they are giving money to people who are not producing, and then they're strangling people who are producing. This is not the right way the country should go. Very frustrating.
It's because the science is focused on the science, and then getting the money is like sales, right? It's become a sales job, and then it's also become who's connected. So being involved in COVID and kind of, you know, people were trying to throw money at me in different ways. You know, like I discovered, you know, as an example with the CDC, right? You know, Center for Disease Control. You have a great breakthrough thing that's gonna kick butt and be fantastic and amazing, and it's like right in your face, obvious, and you come up and you, like, let's say, solve some incredible freaking problem, right? And it's like right there in your face. Are they gonna take it? No. You got to go through one of their. Now the strategy is you have to go through, and I learned all this. I mean, strategic. Basically, you have to do a lot of strategic stuff to get the money, which is silly, right? But in essence, you got to go through CDC. Like CDC is going to give money to certain groups, big companies or big orgs, and then you got to go through them. And big orgs and big names or whatever will take your stuff and then, of course, take the credit for it, right? And then go to the CDC, and then now you create this like loop where the big org continues to get the credit, even though, you know, somebody else is doing it, and it's a middleman, right?
Yeah.
There's middleman and another middleman and another middleman. Like by the time you get your, you know, it's like, oh, you want funding? Yeah, well, you know, like what a percentage of it's going to go towards your funding, but another chunk of it's going to go towards fees of navigating and who's got to get paid along the pipeline for the money to actually end up in the funding. It's really sad that the scientists and engineers and innovators, the actual ones working on the stuff, they don't get direct access. Not it's hard. It's really, really hard. Usually you have to go through some third party that's going to take all the credit, you know?
Yeah.
It's ridiculous, man. Like there needs to be some type of supply chain that we can establish between, you know, the science and research and development sides, you know, because I think that, you know, there's probably ways. It's just that we're so conventional in the method of approach that we haven't really thought about finding that aspect. And I think that you guys are, you know, probably thinking about it and trying to figure out a way of doing it. But I think that would just be amazing if we can create, you know, just a better supply chain for people like us, you know, because it's really frustrating, especially when, you know, a lot of people have, you know, answers to really important questions.
If you think about how much money the government has wasted in the last 2 or 3 years, and every time,
6 trillion,
yeah,
just to be, they printed $6 trillion,
every time they
dude.
put
Right?
trillions of dollars to places which I think is just wasted. Instead of, you know, putting into those money into the waste, why not just give to the people who are productive people who can really do something? It's just frustration is not the right word. Can say the current situation. It's just not only I used to at the time when I was trying to come to this country, I fear America, is the most democratic society. People don't nice, people work hard, and you if you work hard, you get whatever you contributed to the society. But now everything's gone. People lies from the topmost and lying to the bottom, and then doing bad things, and then really if you are trying to do good things, and then people feel that you are idiot. This is how serious this world, this country is. Frustrating.
It is, man. And just thinking about even applications of what people like you and I are trying to develop. They always say it's going to take 10 years. I think it takes 10 years of application, because we have to inform those people in between, which takes the most time. And it's ridiculous. It's like we're able to do the work, but now we have to explain the work that we did to people in between for them to carry it to the top, which takes 5, then takes another 5 years. So it's like everything is delayed from the actual experience. It's like you're affecting reality by adding extra layers of manifestation, and you're wondering why there's friction.
A lot of hardworking companies or scientists, they need funding to do the right work. You don't get it. But on the other hand, government has been wasting money to a lot of things. One ridiculous thing I heard that is during, well, I think it's like 2 years ago, I heard on the NPR radio saying that one guy got $1 billion, spent $1 billion, federal government money, taxpayers' money, built a half a mile wall in the middle of a river between Texas and Mexico. Give me a break. That's so ridiculous. And then that half mile wall probably is gone already. That's $1 billion of taxpayer money. Man,
Yeah, unfortunately, that's what we live in. And then yeah, so it's like, so a new system needs to be there, like one where it draws scientists and engineers into. And I mean, I think there's a way to do it, right? I mean, it's using DAOs and creating a collective and having groups work on projects and then create licensable technology that goes out. When the money comes in, the group that originated gets 20%, and then 80% is resplit among the groups. So if you had a group of 10, 20% would go to the original group. It gets resplit, so they get another 8%, and then everybody gets 8%. Well, then one of the other group goes out, and then they get a win. Then they get 20% of the license that comes in, and then it goes to the others. But now technically they got 2 contracts, really. I mean, they had 8%. Now they're at like 28% plus 8, and then another person pops, they get another 8. So you end up in a situation where instead of winner take all, like the startup culture, like the startup system right now is interesting in the sense that you have, let's say, 10 companies, right, like that are invested in a portfolio. Well, 1 or 2 might be super stars in terms of like monetary success, okay, but the others failed. And most of the time, the number one reason why companies win or fail is because of timing. Actually, it's not because of the team and how smart or not smart they are. It's timing, right? So you have this portfolio of like amazing, engineers and startup entrepreneurs and whatnot, and the superstars make it, and then everybody else has to collapse, and they've been working for like 3 years and sacrificed everything, and then now they're all going to go through depression, right? I mean, this is how it I'm just telling you how it is, right? It's just like your heart is just like all of a sudden it's done. Versus, and it's especially if you're punished, right? Like how shitty is it, like, and this happens more frequent than not, where that timing factor, you're too early because you were too smart for your own good, and you created stuff and you created a platform, and it was just too early for everybody to understand, right? And then you have to stop it, and then like 3, 4, 5 years later, somebody else comes out with something that's pretty much the same thing, but it was just the right timing, right? That happens a lot, right? So instead of like letting all those people disappear, just say, okay, shelf that stuff. It didn't work out. Take those brains and people and then put them into the other startups that are actually winning, and as far as money's concerned, right? Or they can continue their work if that money came into that initial startup and instead of a winner take all went and got distributed among the others, right? It's actually a very simple model that I kind of created, that I want to execute on. But it's just, I've talked to tons of people about it, and everybody likes, like the scientists like it, engineers like it. It's like, you get to collaborate together, and instead of things falling, the teams falling apart and disappearing, they can just fold in within the group and system to the other teams to join in, and then now those teams get like hardworking, great people that just, the problem they were working on is just not ready yet, for the public to consume. um, I think it's doable.
Yeah. So we have talked about so much negative sense. Maybe if we want to continue, we should talk about some positive sense.
Well, I'd like to just interject one thing. I've been listening to this and it's beautiful discussion, but there's a model that's already in place. This does not need to be reinvented. If you um, look at, you only have to look at history to see, okay, where what you just described existed in many, many different small investment banking firms. And you viewed all of the collective as like kind of individual. They could be individual scientists, inventor, whatever, but it was a portfolio of individuals that were very talented. And like Lehman Brothers lasted 147 years. Bear Stearns lasted 95 years. And I could go down the list. And Oppenheimer, a firm that I worked at, is still around after 152 years. And what it is it's collective prosperity. Um, Everybody is accountable for their it could be their invention or their business. Um, and 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 everyone is either rewarded or penalized based on the collective group. This is a proven model. Financial services has leveraged that model and created that model. It could absolutely be replicated in the scientific community. I dropped the mic.
Oh, dude, that's great. I mean, I'm so glad you came up here to talk about that. I mean, because I mean, I'm on the entrepreneurial side, and I mean, I've scaled up, a company, or actually we created the Lash Extension Industries example, scaled it into a franchise system in more than 50 countries, right? And then like did a whole bunch like I've done a lot of entrepreneurial stuff, but in my last project with the OxyKit, it was like a global collaboration project to create oxygen access around the world, like just have it spawn up the education. And in the process, that's when I saw just how bad it is inside of the scientific community and the corporate communities, right? Like here we are, we're trying to solve a problem in the oxygen access space, right? And then talking to engineers, and I'm talking about like the current principal software architect at that was at Microsoft, now is at SpaceX, right? The fellows at Intel, the chief R&D guys, and the chief of residency, like like tons of top people over at Kaiser involved, right? Um, Googles and Apples and Teledocs, and like we got this little behind the scenes pillar tribe thing of just incredible minds, and the same issue kept popping up, right? The scientists and engineers I talked to, when they're giving me information or we were talking together, we had to do this stuff a lot of times behind the scenes, and a lot of us got amnesia, right? But what's the underlying stuff that was really jamming everything was the R&D contracts that every other very interesting thing that I thought was that these top guys at like, I mean, you're talking about the top, the chief architects at these different companies. they're going through the open source channel to create stuff because they're afraid if they go create some tech, even and they want to give it away and they want to help people, and yeah, maybe if it commercializes, they'll actually jump in and actually do that full time. But the route of them doing it directly won't work. If they go through the open source model, right? They can basically, the stuff is open source, anybody's in, everybody's pitching in. It's like liability disappears in an interesting way, right? Because like everybody's chunking in stuff, right? And that was very, very interesting. But all of them are like, they're taking alternative routes because they're afraid that whatever they're doing at home in their garages can be taken by the big company, right? um, they're afraid of talking about anything because they're going to get in trouble under R&D contracts and their career would be over, right? If they could just get the model of just, okay, get these people together, and by the way, a lot of these folks told me, man, if you pull this off, this will be nirvana, right? Where they could all just come in, be autonomous groups, work on problems, create licensable technology that's then, basically, create prototypes and solve problems, and then give it out to you know the next stage, which is like maybe, have entrepreneurs on deck to go find, the create the product pitch, if you will, get demand, and maybe put up a website, get some sales rolling, like the revenue, and prove the revenue model, because that's what entrepreneurs are supposed to do anyway, right? Like, we're supposed to prove the revenue model, find it, and then go give it to, sell it to the companies to scale. If we could accelerate that process from research to prototype to proving market demand, like in this science society, by the way, Gordon, if you go back, there's all these great geniuses and scientists. One guy yesterday was like, did all this tech around sleep tech. Everybody's got to sleep, right? And how, you can decrease blood pressure, and by if you warm up your hands, and your neck is even warmer, 39 degrees Celsius on your like neck, and 32 at your hands, and 27 at your body, you're now going to get optimal sleep, And so he's done all this research about it, but there's that gap of like, hey, take this. I'm like, all right, well, let's just create a prototype and put a YouTube video up there and make some units, 3D print some stuff, basic stuff, and just sell them. They just prove demand right there. Like, people are buying it. It gets going. Then you get the attention of bigger players that way, instead of just like, here's a bunch of like, there's a disconnect. There's the paper and the research and the science. You need an entrepreneur to kind of come in, and a technology style entrepreneur to take that and translate that to the real world and just create a pitch and sell it. And then if we could do this, we could actually accelerate so fast product into market, because if you can create the product autonomously, create a process to take that, and this is actually the biggest missing piece in the work I've done. I'm telling you, there's hundreds of amazing products ready to freaking hit the market. They're just built by people that don't understand. They're not entrepreneurs. They're not business people. They're scientists and engineers, and they're either jamming up against that because they don't know what to do next. And then there's also the regulatory piece. That's a huge roadblock for
Well,
so many.
Myra, the thing you described, I think initially was something corporate America loves to call open innovation, which I find is more of a marketing gimmick. It's not really something they're actually all about, so to speak. It's just something they put out there on their websites, and it looks nice, but it's not something they're gonna probably want to follow up with when something significant is discovered or invented or etc. But there's institutes, there's SRI infamously, they do exactly what you just described. I think the main issue is a lot of this technology goes under the radar. Um, you have entrepreneurs that have this, uh, how should I put it, interest. They have a problem they're looking to solve. They have whatever they have, but at the end of the day, they don't know there's a technology out there that's been invented by a scientist that's collecting dust that solves the problem they're trying to solve. So if you have a situation like that, it's always going to be a gap between the scientists and the entrepreneurs. I think there should be some type of, website or some type of platform that connects all these technologies that are sitting collecting dust, which are are technologies. They're owned by us in America, at least. There are taxpayer funded technologies in many institutes, and they're patented, and the patents are going to run out obviously in 18 years, give or take. So they're really just going to waste. So I think there needs to be a platform. Somebody should create a platform. I think it'd be ingenious to create a platform that showcases technologies that have been discovered, invented, what they can do potentially, they can solve, what kind of problems could be solved by them, and then you have entrepreneurs that understand the problems, because scientists. The issue with scientists and engineers is they don't understand the real world, simplistic problems that people face many times, and they don't have the inventor's mind on a rudimentary level, not on a scientific level, more of a basic level that an entrepreneur would have. So there's a disconnect there, and if you can provide a platform to connect these two groups, I think you could find something very successful. So maybe somebody should get on that sooner than later. But I did want to ask Dr. Ren. Dr. Ren, I feel like I've seen some of your work before. Have you done anything in the uh, electrostatic electrode space?
Electrostatic, electrospace. Can you be a little bit more specific?
Well, I think you've done some stuff with electrodes, right?
Yes, it's a
Flexible,
it's a,
flexible and transparent. I've seen
oh
that
yeah, yeah,
some of
yeah.
your work
The,
on
yeah,
that.
yes, yes. Flexible, transparent
Yeah,
electrode,
I've
right?
seen that.
For
Yeah, have you done any? Have you done anything with electrostatics and electrodes?
not really. No. What we have been doing, those were earlier work, transparent electrodes for flexible electronics, wearable, foldable, those things. And then recent years on the extended to that is we have been doing catalyst for water splitting, to basically convert additional or oversupplied power into hydrogen to store energy, that kind of thing.
Okay, but nothing with utilizing the ions, electrons to turn them into, or utilizing them in general at all.
No, not really.
Okay, cool. Because I'd be giving you
Hey,
a
Denny,
call if you did. We'd have to talk if you did, but anyway.
Denny, I love what you're talking about. This is a thought that me and a couple of my friends were talking about too, is just creating some type of database with supply chain data as well, to where we can, basically go over everything that's going to have to be changed over by 2030, and just take it supply chain from to supply chain, and figure out how we can introduce alternative, technologies and materials to these supply chains. I think that would be a great starting point.
Well, Kenny, the issue is also that a lot of entrepreneurs don't understand a fucking word in a scientific journal. So they're very big words in there. That's the best way I can put it to you. So a lot of times they'll describe what's happening and what they're doing and what they're solving, the scientists, and the entrepreneurs just don't understand what's being said in that paper. They just don't understand it at all. I mean, if they could break down what's been done in a layman's term and put it on a platform where somebody can type it in like Google, like a typical entrepreneur, like Mar, for example, who's an entrepreneur that could be solving a problem. He could have seen something and he's like, oh man, if I could just do this, I could make this product, and he could have a platform to research that. And I think the disconnect in the on the kind of book, intellectual level, on a book level, because scientists are very smart, book smart, but entrepreneurs are very street smart. I think that disconnect also is a major issue, because a lot of times when you read these papers, you just half the time you don't understand what's being said in there until you really dive in and to spend time, which a lot of people don't have these days. Corporate America, if you send an email that's more than a couple sentences, good luck having anybody read it. So the bottom line is, I think there needs to be some layman's description of what's happened, of what just was accomplished by these very smart genius scientists, to a layman entrepreneur who could be looking to solve a problem that this technology is a perfect fit, but he just doesn't know that it is, because he can't understand what just was done. So that's a whole other thing, and I think there needs to be some connection there. And if it does happen, I mean, there's so much technology that's collecting dust that our government, institutes in our government and universities have invented, that it's just phenomenal technologies out there. People would be shocked.
I think that you can use maybe a translator, so think about if it's an app, just think about how Uber is. There's different services that you can provide in that app, to where if there's somebody that, just published a science paper, You can have a translator, bid on that basically and work out a, layman's term explanation for the entrepreneur. That's really what we've all been thinking about, is just trying to figure out how we can create a step-by-step process. But I think that it's definitely doable with data scientists. If we put the right team together, I think that we can probably pull it off.
Well, there needs to be a platform.
It's
Somebody's got to
it's
make that
actually
platform.
dude, I've been studying this at like most of the people on stage we've talked about, like, whether it's Eli, Katerina, Joyce, probably, I'm sure she's been there, Kyle, like we've been, like, Peter, uh, hundreds of people, right, about this. What I've discovered in my user elicitation of the engineers and of the scientists and of course of the entrepreneurs, because I'm in EO and surrounded by thousands of them everywhere. Everybody wants a place to live. That's what's interesting. Like, they want to be together. Like, that's what people really want. They want, like, it's nature place that they could live together, have a maker space, have a lab, and have the teams working on, because they also don't want to solve the same damn thing, right? Scientists and engineers want to work on different problems. They also want, like, they're working on something, they want to go jump over and look at another team's thing, like, oh, that's cool, and then put their input in there because they like to solve problems, and they want to solve problems, and once the problem is solved, they want to go to the next problem. The entrepreneurs, same way, right? Once I mean, an entrepreneur's dream that doesn't exist yet, which I plan on trying to make happen, is the ability to have exactly what you said, which is like, but an actual space and admins and everybody underneath, in a support structure of administration, to support these two primary characters, which is the scientist engineer as well as the entrepreneur, right? To just go in there and be like, yeah, let me just pick this product up and take it to market, right? Or as it's being developed, right? Be involved with the scientist and engineer at the beginning stages, so that the scientists and engineers are building things that the world actually values, right, and wants. So, and then along that process, because if you put a scientist and an entrepreneur with inside of a lab with an engineer, and then they show them what they do, oh, here's the thing, well, what does it do? And then entrepreneurs are usually pretty good at asking questions, right? Like, yesterday we had a guy up here with um, what he had, like the sleep tech that I was talking about, right? And it was all, it's like he's like trying to go through the mattress companies. It's like, oh, go through, then the mattress companies are already making money and they're printing. And I was like, yeah, but this is also complicated to go through the mattress. You don't need to. At the end of the day, what you're trying to do is you just need to warm up. You need to warm up the hands, warm up the feet, warm up the neck a little bit more, and then put the body a little cooler. You could probably do that with some type of a blanket, right, that you put on top, or some type of something you wear, that you don't have to do a big old huge mattress. And a mattress you're going to move around anyway. How are you going to control where the hands are, right? So the practical stuff, like, I see that kind of practical, like, okay, they're going to be flopping around on the bed. You can't really do that, that's too sophisticated on the bed to be trying to catch exactly where the hands are on the bed and change that setting to be warmer than whatever. So every time you're moving around, that's way too complicated, right? You could do that with some type of a anyway. So we started brainstorming around that kind of stuff, right? But that's, I mean, that's what we got like, everybody in Clubhouse wants to, like, all the brains in here in Clubhouse would like that. And the thing though is, most people when I talk to about this, especially on the entrepreneur investment side, what do they want? They want to control it. Like, this is brilliant, great, let's control it and monetize off it. No, and it's like, the trick is, how do you create a system where it kickstarts and gets going, and then you only have maybe a handful of scientists and and a couple entrepreneurs or something working together, and then as they produce licensable tech that creates the revenue, then they grow, then that system grows, and then that
Well,
money stays
Mark,
within. Yeah.
but I don't think entrepreneurs are the issue at all. I mean,
Yeah.
entrepreneurs are not the issue. I think it's the conversation you guys were having earlier was very interesting regarding the large organizations, whether they're corporate or government organizations, basically, the secrecy and stifling the technology. Anybody who's dealt with corporate America will tell you there's a reason why they've never truly fundamentally innovated. They do incremental innovation at best. There's no large company that's not founder led. There's no large founder led company that's ever truly innovated. I'd love to see an example. Everybody has one, but it's always incremental. And I'd love
They
to be
just buy
proven
it.
wrong.
They buy
Oh,
it. They
I
buy
would
it.
love to be proven wrong. I've been looking for this for many years. But the thing is, they do incremental innovation because once the founder leaves, I mean, Jobs broke it down best. You have a situation where you have a bunch of MBAs. These guys are taught to,
Yep.
cut costs. That's it. I deal with these guys. Whether you name a company, I've dealt with them. And these
Make it
guys, they
annoying.
don't like innovation. Innovation changes things. Innovation creates uncertainty. Innovation creates a situation where they're bringing something in that could potentially be great, but it could potentially be bad too. So until it's fully proven, especially in this day and age with all the risk involved in the world right now, they're very risk averse. So I would say corporate America is the last place to take anything innovative to. And the last people you want to deal with is an MBA who works at Google or Apple, who's making $500,000 a year salary alone, and et cetera. He's not going to risk that for anything. There's nothing he's going to risk that for. That's remotely risky if it's not fully proven, and even in the market, really.
See,
So
that's what I'm saying.
it's really a corporate America issue. It's not an entrepreneur issue at all. Entrepreneurs are looking for the opportunity. We're dying for the opportunity. We'll risk everything for the opportunity. But the MBAs, the guys that have never done anything, outside of getting a paycheck, they are the ones that stop innovation without a doubt. I deal with them on a regular basis. They don't care for innovation. They care about their job. That's the only thing they care about.
and you're right, and that's what I'm saying. That's the problem, right? So, okay, right, I'm glad you clarified that. Okay, so what I meant to say, right, just to be clear, okay, you got product, you got the product development pipeline, right? So you got research, then and then you got prototyping, and then everybody gets stuck at like what happens is they create a little prototype, or or in science a lot of times they even don't necessarily do the prototype, they do the research and they're in the lab, right? And then now you did all this work, you just need to do a prototype, and then if you got a prototype, it's like right. The missing piece is to take that prototype and rapidly, right, very quickly, and then have a systematic approach. Like if you sit there and you like have a systematic team, is like create the stuff. All right, cool. Let's create the prototype. All right, now let's go do the same freaking thing. Especially now, I'm a digital marketer, right? Create a prototype, create a YouTube video, put up an e-commerce website, have just chunk that in, and you have a team of customer service reps that are going to sell the thing, sell the thing. You got a pitching entrepreneur who's going to pitch it around, and you just need to show revenue. Like once you show the revenue and the market size, okay, like look, here's a bunch of customers, they bought it, and it's
Yeah,
growing.
they'll pay 100 times more for it once you do that. They'll
Exactly,
pay a million times more.
exactly.
You know why? But why? Because their
It's
job
proven.
is
It's
not
proven
on the line. They
because
know
now
that
the
they will not.
MBA.
There's no risk. There's no risk for them at that
Exactly,
point.
exactly,
That's really all
exactly.
it is.
That's how it is. Exactly. Because the MBA wants their
De-risking.
bonus.
Yeah, it's all
The
about
MBA
So
wants
even
their
it's all
bonus.
about these little dictators that run these little departments,
facts.
and
Exactly.
their jobs say innovation, and they're supposed to be taking risks, but they will not take a risk. It doesn't matter who they are or where they are. I don't care if it's Google. I promise you, they will not take a risk.
But
Never.
look what they do. They buy companies that have proven the revenue model, right? So you don't have to go 10 years. You just build the thing, get some revenue coming in. Any freaking if you got and if you package it properly, like here's the revenue, and you show the metrics, you know what you're talking about. You know how to talk to these MBAs. You're like, all right, cool. Look, we already did the model. Here it is over here. This is a service based product, right? So it's local based and whatever. So we put it through our local go to market engine, right? Process where you got people going that are just going to take the products that are coming out, the services, and push them out there through this process, which is all the same shit, right? It's like you got a service, you got a product, you got a part, whatever, right? You got different categories you target. And then once you put it through there, you can easily, like within a couple of months, 2-3 months, right? Show here's the revenue, here's the referrals. If it's a recurring revenue product, that's the magic, right? Like here's the recurring revenue. Here's how sticky this is, and it's growing. And this is this market. And by the way, if you extrapolate that out to the world, it's that kind of market, and it looks like that. You create an auction between different companies to come in and bid and pick up that. Literally, not just tech, right? It's a little step further. It's proven tech. It's tech. It's revenue proven. Like there is demand because look here, like even if 100 people or 200 people or 250 people, or depending on how, even if it's a small $20 thing, like 1,000 people bought the thing, right? And you show growth there, they're gonna buy that, right? Because they're like, okay, people bought that. That's proven revenue, and it's like, hey, it's revenue. Now you do your job. You're a channel. You're a big ass
Yeah,
company,
Matt.
and here's a product, pump it through your channel, right? So
But before Yeah, go ahead. Sorry, I thought
Yeah,
you
so
were.
yeah, I'll just finish by saying that little small step of you don't have to build the whole fucking company, dude. Just build the revenue model to prove it, and then have the big company buy that, and they'll buy it at like crazy X multiple because it's a strategic buy. If you're smart, you're like, hey, this is a strategic buy. Here's how big your channel is. You can make this money. Here, take this license, give us a royalty, and we don't want to fuck with it anymore because we want to go solve the next problem, right? As entrepreneurs, it's like, here you go. We package it up. You do the deal, right? And then you go pick up and then now instead of going into depression after you sell your company, because that's what entrepreneurs do, their whole family and everybody, their whole family is the company. They sell their company, they got this money in the bank, and guess what? They go into depression, right? Because they just lost life, really. Okay, now they could come back in and have a whole slew of new products to jump in and take to market or whatnot, right? So that's the model I'm talking about. Don't build out the
But
company, just
before
prove
all
the
that,
revenue
Mar,
and sell it.
but before all that, what you guys were talking about, Dr. Ren and whoever else is in this room listening, if somebody could just create a simple Google that translates these research papers and this innovation that happens constantly in the scientific community for a layman entrepreneur to be able to go in there and he's trying to solve this stupid problem that could be a massive product for you never know, and he could just look for this, type in what he's looking to solve, or maybe just research the keywords the way you can research a patent. A USP to a website, you could do keywords, and obviously it's a little bit of work involved. But if you can create something like that, I think that would be phenomenal, because entrepreneurs are always willing to license, especially at the early stage. They're more than happy to license because they don't have the capability to create this innovation. They don't have the skill set, etc. So they're more than happy to license it. And I think if somebody could create that platform, man, that'll innovate, that'll boost innovation like nobody's business.
Dude,
Well, we are
I
kind
really,
Yeah,
of
that's what we're
I
doing
talking
that
about.
a
really
little
feel
We're talking
bit
like
about
we
here
could.
with Science Society, because it's just an audio version, right? So people told me I should have transcripts of the thing and kind of edit it at some point. But that's exactly what we're doing. And if you go on our website, there's a huge amount of, um, current cutting edge research explained in a way that everyone should be able to understand it. So that's exactly what we are doing, just in an audio form, but we can easily transform it into a written.
Make it like Google, Katerina. Just copy Google. That's it.
So,
Just let me Google a stupid problem and show me show me the smart solution.
so Denny, here's
Love,
the issue.
I would love
Here's the
that.
issue. Here's let me tell you guys the issue that we faced. Okay, because this is something that Katerina and Eli and Kyle, like Denny, I think, you're new to this and to our little class talk this bunch.
You're breaking up
But
for me, Mar.
the
You're
problem
you're
is,
You're in the
Matrix.
matrix, man.
oh, okay. Am I back now?
Yep.
Can you guys hear me? Yeah. Okay. The problem is that it's the problem I'm trying to solve is figure out how to spin these up on ultra low cost money where you don't need investors, because investors want to come in and at the end of the day, VC funds and an entrepreneur, it's all about economics and control. Those are the two things that matter: economics and control, right? So investors want to get cash out and 10x and all that other stuff. That's not what's needed. What's needed is for a sustainable system of innovation that pumps out money that comes back in, that's sustainable, in which the entrepreneurs get paid and the team members get paid in this kind of collective format. And it's not a
But that's not free market, Mar. That doesn't match our
no,
system in America, at least.
no
Well, what about
it's
the data?
hold on.
Why
You
can't
didn't
you
hear
just
you didn't hear the model
It
earlier,
would
right?
need to be a non-for-profit, and then it would match the
Yeah,
system.
if it's not for
It's for
profit,
profit. No,
if
hold
it's,
on.
yeah,
It's
it could do
no. If it's no. Just to be clear, it's
that.
for
Mar
profit.
said, no,
Okay,
no, no, no,
like
no,
the
none of
engineers.
that, none of that.
Let me be 100% clear. Okay, the engineers and scientists need to get paid. Okay, they need to not be
facts?
slaves anymore. Okay, that's what it comes down
Well,
to,
they
right?
would
Like,
get
so
paid
the
in
way
a
I see it is,
not-for-profit. I mean, it's
Yeah,
not like
yeah,
they wouldn't
yeah,
get
yeah.
paid.
Look into the non-for-profit. They do get paid. You can still pay people in a non-for-profit. I would look at the actual structure of this, because capitalists in your own country have utilized this system very well.
well,
And it might very well work for what it is you're talking about.
it's really like think of an employee-owned structure. That's what we're talking about here. Okay, it's really creating an employee-owned structure.
Yes.
You
Just
know?
like that's what the old investment banks were. They were employee owned, and
Co-op
and
basically,
they
right?
and every employee had a stake in the business, and that could be every inventor, every and the reality is that what you're talking about, actually, there's a place in Atlanta that's about as close as you're going to find to what you're describing. There's a lady by the name of Robin Bienfait, who was a technologist at both BlackBerry and at Samsung, and her sister. And they created a space, an actual space here in Atlanta that and there are inventors in the space. Abso-friggin-lutely, there are inventors in the space, and there's a lot of collaboration going on. And what they're looking to do is create commercial products, commercial technologies. It's actually very cool. And what the ladies do, because they're very savvy business people, is they've created a small team of different people that can come in and really look at something and say, well, I think we have a much better chance going to market this way. And almost all the businesses are bootstrapped. Um, they do have to. They are looking to create that revenue themselves, and rather than take on investors or maybe get in bed with people who could stab them in the neck later, more like what you said, Merritt, like I think the model's beautiful that you're thinking about. It's you take a group of technologists and a group of great marketers and people who really have connectivity in the world to bring unique products to the market. And yeah, so you can create it, license it out, go back and create, rather than like going through that vicious cycle of having to raise money, having to take on investors, having to deal with all that complexity. No, just license it, get it out, and let's go back and invent more. I think a
Exactly.
very realistic and beautiful model. I think someone's really
But but
should
Gordon,
try it. I think it
Gordon,
Gordon,
works.
Yeah, and it kicks
are
off.
you're familiar with you guys are but
It kicks
Mark,
off.
you guys are familiar with
It kicks.
Stanford
Oh, go ahead. Sorry.
Research Institute, right? But you guys are
Yes,
familiar with Stanford Research
no
Institute.
doubt.
That's yeah, they spun out, Siri. That's where Siri came from,
Yes,
SRI Siri.
yes.
That's where the computer mouse, if you're familiar with the computer mouse, the internet. These guys have been involved in everything, and it's kind of like what you described, and they are government entity, technically speaking. So, but they do spin out the tech, and they do this. But at the end of the day, I am very familiar with them, and it does seem that corporate America is kind of a shrouded in secrecy these days compared to before. So it's gotten a lot harder to do with what they do and try and this model in general because of the way corporate America has gone lately.
And with this model, what's nice about it, the reason I like this, and being disciplined and sticking to a license, like it's a pseudo. It's like let's take the tech and push it to market to prove the revenue. Like you could prove revenue really freaking simple these days. You just throw up a website and put a demo thing and create a prototype and 3D print, even though it might be expensive. I mean, even if it was expensive to make the first units, even if you fucking lost money, right? Like seriously, right? Even if you lost money, it doesn't matter because everybody knows if you produce units at scale is going to be lower at cost. If you're just focused on proving the demand and that people are going to buy it, and that there's going to be, especially if there's a nice recurring piece in there, that's super juicy, right? Right? If you can prove that at a small scale, but show that it's a massive market, people will buy that all day long,
Well,
dude.
if
They
you could
just
do that, Mario, you don't need to do anything after that. You got money showing up at your front door when you do that. Yeah, that's
That's the
easy.
whole point.
Things get a
You got
lot easier once you
predictable.
do that.
You got
Once you
that's the whole point of the model, right? You got predictive revenue now coming in, right? You got predictive revenue. There's probably like a big ass check to come up front with the deal, right? It's like, hey, hey, this is great tech. We proved the revenue model. Here's like, 5 million at close for this, right? And like, whatever, 5 to 10, anywhere between, a few percentage to 10% to 12%, 15% maybe of the tech as a royalty, depending on the specific technology, right? And then you now have you're disciplined and you're like, all right, we got this big ass money. What do we do with it? We don't just go buy yachts and stupid shit. No, it goes back into the collective, right? 20% goes to the team that originated that revenue piece. Okay. So now they could go buy their yachts if they want to, right? Or whatever they just do whatever the hell they want. What are scientists and engineers going to do when you what are scientists and engineers going to do when you give them money? They're going to go buy lab equipment and they're going to go innovate even more.
Right.
And they're going to like that, right? What are entrepreneurs going to do when you give them money, right? They're going to go try to find the next thing to sell, right? Just because it's fun, and that's what we want to do. And we get and this space of people are super smart and get bored, right? Most people want to have a consistent thing, right? Like they go into work and they got a consistent check and they do the consistent thing. They don't want to learn new shit. They just want to do the same thing. So they go home and watch their Netflix and do their ball games and whatever, right? Okay. Um, Not the group of people I hang around with, right? And that are in here and the scientists and engineers. Opposite. They want, as soon as they solve a problem, they don't want to do it no more. Dude, I've built companies straight up. Like I built technology and went out and like turned it on and did $90,000 month one and then turn it off because I was like, oh my God, I'm gonna have to go grow this into a franchise system again or a big ass global system. No, I was already a CEO of a company doing franchises in 50 countries. I'd never want to do that
Welcome
again.
day.
Okay, I was very successful. Never ever want to do that shit again, right? That's boring as hell, man. That's just people management and HR management and litigation management for like a lot of your stuff, and then you're managing cash flow and it's just the MBA shit. It's like give that to the fucking boring ass MBAs, right? Okay, so there's but they want to solve different problems, and entrepreneurs want to take something to market, and as soon as they take it to market, improve it, sell it right away to and have like some M&A attorneys and like a pipeline for them to actually go take that tech, prove it, and then go right away sell it and exit. They would do that over and over. That would be great if you had the support structure to do that, right? So that doesn't exist right now, and so I've been basically building a massive collective. And in essence, I kind of went through this process. I did the open source thing. I created this OxyKit oxygen concentrator, which the whole darn world started building. And I got a award from President Biden for doing this, right? And congressional award from Vegas and Tata Consulting Engineers, the biggest company in India, took this and validated it. And then like 50 companies just spawned up overnight making oxygen concentrators, right? I did this process through a free route to save human lives, but in so doing, I saw how powerful this process is, attaching some lawyers and licensing agreements, and just solve the problem, scale it, give it out, and then go solve the next one. And you could create. Once you have a hit, then you grow. Then you bring on more engineers in the team, more entrepreneurs. And why should you bring them on? Well, because they might have a big hit and they're going to share the revenue. We don't know who's going to be at the hit. Nobody knows who's going to be the hit in there. But if we're all working on something and something's going to hit big, and we go help that team hit. And if we don't hit, well, we could go jump on one of the other teams, right? It's forming a collective of the scientists and entrepreneurs together, and then growing in a disciplinary fashion based on the revenue that comes in.
I love it, man. I kind of have like after what you were talking about with the technology for the sleep aid and stuff like that, that kind of made me think about a question to ask Ren. Is there a way of making biosensors with these crystalline structures, and can they be applied to fabrics to where we can code the fabrics to give them applications that we can kind of code, if that makes sense?
Yeah, of course. So a lot of applications can be looked into and put into a real product. And speak of the way you guys are talking about, there's a need. I fear that there is a huge business opportunity you can think of. I'm thinking of this way in a way, mortgage company. You have so many banks, you have house buyers, and then there in the middle, there is a mortgage agent. What their job is, then look for different company, different banks, different rates, whatever terms, and then to work with the buyer, home buyer, and as soon as they sign the mortgage, they sell it to a different bank or like that. So I feel that the similar sense they should have a technology agent. If you can start a consulting firm, hire a lot of bunch of PhDs, it's sort of technology consultant or agent, and they just go to different companies, look at their needs, company ABC to E to Z, whatever companies, and each person responsible for either a certain domain of the technology or a certain number of company, and then look at their demands or their needs, and then they come to look at the universities, their intellectual property office, whatever the inventions they have. Or first, they can just simply do a web search, whoever is doing this kind of research, and then nail down a few, two or three good people who has published very well in that domain, and then go to that university, talk to the IP office, say, I have a demand here. Show me your IP portfolio. And then if that person can match with the company, and then, as an intermediator, hooked up the technology to the company, and then problem solved. You take whatever you ask for, commission based or whatever based, and in that way, it's a huge business. I think there exists.
Well, I'm allergic to consultants, so I'm not familiar with the space. But Dr. Ren, isn't there probably certain groups and consulting firms that may be doing this, or is it not at all happening?
I don't think so. What really is happening, each university, they have IP office, and they don't have too much money to really commercialize or advertise their IP. So if I figure out if you have such a kind of company, really as a technology agent I was talking about, can act as an intermediate people and between company and university inventions, that would be a huge
It's a very
business.
smart idea. Yeah, no, 100%.
Basically, there's just a ton of tech sitting there, and
Nobody's touching it.
actively
Nobody
advertising.
even knows it
Nobody's
exists.
actively.
Nobody even knows it
They don't know.
exists.
No, yeah. Nobody, and then the guys who made it don't know how to, like, that's not what they do, right? So there's no like active advertising of like, hey, we created this new tech. It's just like, we created this new tech,
Well,
now we're
they do
just
press
waiting
releases,
for
Myron,
some
but nobody ever sees them, and they go under the radar. So it's one of
exactly,
those,
right.
corporate press releases.
Duck go or something, right?
Yeah, it's
And you can,
For us in the university, most 90% of the people, of the university professors, they just pursue whatever is the best in the world, and they do research. After the end of the research, most of the stuff they just publish it. University has a saying, either publish or perish. You have to publish. After publishing, and then they move on to next project, say whatever interesting. And only a small percentage of the whatever results, inventions, ended up into a patent application. And the patents, USPTO issued so many patents every year. Only 3% of the patents issued patent ended up into products. So there is a huge amount of technology and never been tried for products. So that's why I was saying, if you guys are very smart as entrepreneurs, and you should form some kind of company, and it just acting as an intermediator, and then basically try to advertise, try to take the university inventions to whoever the company needs it. And there are existing products, they need improvement, and here are the inventions that will improve your product, make it much better function and at a much lower cost. That's one kind of business. The other business is there are also entrepreneurs. They want to start something, some new product. You can also hook them up. Hey, here is a university A. They have this very good technology, and they can make good products for some applications. You guys have you probably can take it and try it. So all sorts of those things, and then if it can be done, would be a very good, successful business, I would say.
I would
Okay.
think trying to deal with universities and their intellectual property portfolios and getting them to like take action, and I mean, I think you'd be slamming your head against the wall. The bureaucracy, the fact that one person could make a decision to upend. I mean, it's like dealing with Intel or dealing. I think it very cumbersome, very long lead time. I think that's a hard model. I think a much better model would really be like what Mayor wants to do. Bring a community of inventors together, let them do what they do well, but have a group of business people, marketing people, people who have taken technologies to market, and collaborating together, because I'm very entrepreneurial. Came from Wall Street, but also have been on Main Street and have created ventures from scratch, and have gotten medical devices into Mount Sinai. I mean, but those were more like luck. So I think the real traction is staying away from the large institutions. Unless you've got time and patience and are willing to, slug it out to maybe get a result that's good. By the time you do that, you could have invented and got other things into the market and be on your third or fourth thing. That's my only comment about dealing with universities.
Yeah, and the other issue is from my experience, if you are an entrepreneur that doesn't have the credibility or the name, so to speak, or the background, and if the company's not up and running fully and you're not fully staffed, etc., it is a bit of a back and forth. It could take many, many months at the fastest to get something done because they want to license it to somebody that can do something with it, so to speak. If there's no credibility there, just because I
A
had a
lot of
buddy,
show and
yeah,
prove.
yeah, I had a buddy,
You're
yeah,
right.
who's, yeah, he doesn't have the background. He's never had anything out there, and he tried to go down this process, and I was helping him, and I actually, kind of flew in to take the meeting with him to just kind of, I was on the board of his company, so just trying to help him out, and we convinced them at the end of the day, but it was not easy. They want to get it off to a big corporation. They don't want to get it off to Joe Schmo in the middle of nowhere.
Yeah, I agree. Like this, I mean, dealing with bureaucracies and all that. Yeah, forget that. Just if you have a group of scientists and engineers and some 3D printers, okay, you could just say, let's tackle this problem and make a little widget a little bit better. And there's a huge market for that. You could probably just target a few products real quickly, make a few things better, create the widget, slap up a website, sell a few widgets, and then license that shit out, right? Like that's it. And then now you got revenue. It's like, okay, here's the fun, big, hairy, audacious goals that require a lot of money, and we want to do. Okay, let's just go do some little simple thing to go create some license revenue. Like you can have a team. I mean, I know this is what I do. I mean, very simple. You just go to like viral-launch.com. You can just identify all the different, uh, grow products all over Amazon, do analytics, and kind of identify areas to target, right? And make a little bit of improvements. Like like it's like, hey, we need money, right? So it's like, let's go target high margin stuff. Like for example, a telescope is like 10x as an example, right? Simple beauty products are like 80% margin. I was in the beauty business, right? So you could target like you can have this like stream of, hey, let's solve these simpler problems to generate the revenue and constantly have like licenses coming in from that tech, and then we got these big, hairy, audacious goals that everybody really is working on that are long term, right? Whether it's like climate change stuff or like big stuff that requires a lot of money. Well, let's create an engine and bring that money in and not have to ask anybody shit, right? You don't have to beg anybody. You don't have to wait a while. You don't have to have approvals from people, because that's the problem. The problem is you just need an engine to generate consistent revenue that's coming in to the scientists and engineers without all this bureaucratic shit, right? And the easiest way to do that is make something, forget everybody's will this work, will this not work, just go straight to the market with it. Go straight to the market with go instead of talking too much. How do you create a basic prototype of this technology and get it out there and get some sales and prove revenue? And then now you got everybody's attention instead of wasting all that time talking about would it work? Do you have a company? How big are you? Are you going to be successful or not? Or blah, blah. Just freaking the guy will show you he's successful if he goes out and sells some shit, you know? Right? That's how that's what's missing. I see as far as I see it.
The only
That's kind of cool.
problem is with this model is that most of the scientists that we have here that do really innovative stuff are not Americans. And they don't necessarily, everyone has a green card that can freely move around and work wherever they want to work. They will have to work for an institution that can provide them a visa and finance it and get visas. And as a university, it's really easy, especially J1s and also H1Bs. But for company, it's really hard. Like J's, forget about it, and H1Bs is a lottery. Even if you pay for it, you don't necessarily get the visas for the people, and this is a huge hurdle. So you don't necessarily have all this innovator engineers and so on that are really good and doing this type of work available as a private company. And then the other thing is the idea that Dr. Ren has, what is good about it, you basically um, have all this huge variety of people working in this high technology, expensive equipment background that you wouldn't be able to pull off kind of generate that type of diversity of brains in a company. So that's the up and down side. But in general, I like both, but just a few things to keep in mind.
Yeah, I mean, but I think that would be a function of like hiring and having on deck a good, just an attorney,
Immigration lawyer.
just an immigration attorney, because the big companies.
I know a great one on Clubhouse. We'll call him
Yeah,
in, ping him in here.
it's. I mean, the big company. They're just using.
As a company, you don't get access to all these visas. Like there's a limit of visas every year, and as a company, you don't necessarily get access to them. That's just
Well, I can,
not even with the best lawyer.
I can guarantee you, I can guarantee you, if there's a group of scientists that get together and a group of entrepreneurs that get together to do this, those group of entrepreneurs, if we got a few of them, like myself, we will figure out the visa. Like when you were mentioning the visa thing, I'm like, yeah, that's easy, right? It's like there's a process for that. That means there's human beings for that process. As entrepreneurs, that's our job, is to understand how things flow around through human beings. So if there's human beings in the process, and like I'm an entrepreneur, it's my job to figure out how to hack the system, right?
I know a guy that knows a guy, basically.
Exactly. That's just how it is. Being legit, right? So it's like, how do you get in the system and legally hack it, not illegally, legally hack it, right? And by hack it, I mean you just don't wait in line, like, you know, I'm not gonna go, like, if I ever wanted a job, I'm never gonna go fill out an application to get a job. I'm just gonna walk in and make my own job, and it's not gonna be I'm gonna get paid a salary. It's gonna be like, hey, here's what the problem you have. Here's the solution. Here's how much money it could potentially make, and then create some type of avenue where it's not going to cost them anything probably for me to get in and do my thing, and then but I want to share on the upside, right? That's how entrepreneurs think. They don't care about the salary thing, right? They just want they want the big win, right? And it's not necessarily about the money. It's just like the big deal, right? Like to have big impact. That's their primary
Yeah,
driver.
and Katerina, which one is it though? Is it good that America's bringing the brains, or is it bad? Because earlier you were saying it was bad. So
I'm not saying it's bad. I'm just saying it's how people are being treated, being arrested and stuff like that for ridiculous reasons to collaborate with their home country, to go back and analyze data in their home country while they are there visiting family. Those are the ridiculous things. And I'm not labeling it, it's just a fact. And, and I know that a lot of companies right now are having exactly that issue to get good minds and good scientists that actually come into the lab and don't work from home without visas. it's really, really hard to get those people, and even big companies are having currently issues with that. So, and I don't know, it's, if a huge company like that, they didn't find a way around it, that has like billions of dollars, and I don't know, makes COVID vaccines and stuff. I don't see how, you just pass over it, these problems. Like, I don't see that.
So Denny, you weren't here earlier. Like, okay, so basically, Dr. Ren talked about. I guess there was some other doctor that had done some work, and then he's from China or something. Investigated it.
You're in the
Maybe it's
matrix,
telling.
matrix, Mar,
Oh
matrix.
man. Okay. Am I back yet or not?
Yeah, sounds good now.
Can you guys hear me? Okay, so hey, Dr. Ren, can you maybe tell Denny what you're talking, because now this freaked out all the scientific community, and then unfortunately, like we got a lot of Chinese people here, or from Chinese origin, that are Americans, right? And like we should really treat them well here, especially given the tension with China. And I imagine most of them probably, like myself, I'm a Syrian, and I came here when I was 5. I consider myself an American. I've been here my whole life. I'm an American citizen, right? I don't, and a lot of folks that have come here consider themselves American, and if they're going to be targeted because they're Chinese
Well,
scientists and
China's a
engineers.
unique case, Mar. China's a unique case. I spent a lot of time in China. I have a lot of respect for the culture. I have so much, I can't even tell you how much. But China's a unique case
No,
because of
no, I get it.
the competition that's ensued now.
No, I
It's
don't think
not
it's just
just
competition.
China.
I think,
Portugal is not a competition, and it's stuff like this. Not
wait,
he was not
Katerina,
arrested, but
hold on,
he got
hold
also
on.
in trouble. It's not just Chinese. It's
No, but what I'm talking about is the inevitable. Like Katerina, trust me, the Chinese people here are probably are going to have a lot of problems coming up, right? If especially if we don't do this right, because like in my opinion, not in my opinion, in China's leadership statements, they want to be the global power. Okay, so to be the global power, you have to go to war with America. That's just fact. I mean, that's just how it is. If you like, America's a global power. The way you become a global power, according to historic precedent of
But
human
the
beings forever.
scientists have nothing to do with that, and I
Oh,
don't
you're right.
know
You're
why
right.
we
You're
are
right.
talking about like some war stuff in the science room, because we have nothing to do with it. I don't have, my colleagues don't have. So we work, and what I said earlier was that we have been educated for free for the U.S. By our home countries, and the U.S. is harvesting all these mines around the world because it's kind of attractive place to be. It's good for your career to have worked in the U.S. at Harvard or whatever, and they use it, and everyone would use it. I'm not saying it's bad or good, but the least you can do if somebody is working here as a PhD student on a minimum wage, or and they really actually work and do great stuff, and or as a postdoc after going 10 years to school, and you work maybe for 40 something thousand or even less a year because you're dependent on a visa, and there's way more stories, then at least treat people right and don't arrest them, and
Oh,
and stuff like
I
that.
Well,
agree.
Mar, real quick.
Well,
Katerina,
hold
the
on, hold on.
only issue with can I
Let me
say one
clarify.
thing?
Let me clarify just for 2 seconds, okay? Mike, Katerina, what I'm saying is, unfortunately, the United States right now has to make a rational decision of treating foreign scientists and engineers like gold, okay? Because in my opinion, first of all, you just got to look at the facts, right? We're 5% of the global population, okay? We need to do everything possible right now to bring in every brain we can into this country and treat them really, 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 really well so that they stay here, right? Because we're only 5% of the population, right? And the world is changing so fast, and we're not going to have the competitive advantages, right? And the only way you're going to have competitive advantages is if you have all the brains, right? Wherever the brains are going, then you can maintain competitive advantage over the world, right? But if you screw up and you start throwing people in jail because they're Chinese descent or foreign descent, then you're gonna screw up your whole country. Like that'd be like the stupidest thing this country could do. That's my point. There is like it should
So,
actually be. They should treat them very, very well and have a process for making sure that they feel safe, they feel comfortable, and then they don't flip on the other side, and that they stay on this side
Yeah,
kind of
and
thing.
to do both sides of this thing, so I can agree with everything you said regarding the treatment of science, etc. But we do have to keep in mind the espionage and the stealing of United States intellectual property around the world. This is, a place where everybody comes because there's opportunity here. But Katerina, keep in mind, when you say we're harvesting and you got this education from your country, um, we pay for your security. So without us making sure you are
What?
free
Why?
and
How? I was
secure,
safe in my own country.
you
What?
wouldn't have the social programs in Europe you have if America
What?
didn't protect Europe
I
the way it
do.
protects Europe.
What? Europe doesn't protect you?
America
What are you
protects Europe. That's the fact. That's an undeniable fact. And without that high spending in military that we do, Europe would have to spend a lot more in its
about
military,
Europe?
which would
The
then
US
not have enough for social
That's the
programs the way
first
you
thing.
guys spend.
We always built on giants, right? So don't forget the history. Without Europe, there wouldn't even be a
Well,
US.
everybody would be
So
speaking
that's the
German
first.
potentially or Russian without America over there. Keep that in mind.
I
No,
think
not
I think this is
necessarily.
too much into
Uh,
politics.
Well, it's
Yeah.
not
But
Yeah,
political. We do pay
let's
for the
change the
seriously,
security of
conversation.
Europe,
Yeah,
but yeah.
how are you
yeah. I
paying
think
Let,
for the
when we talk
security
about
of
these
Europe?
situations,
Well, because we have our military
just
station there
quickly,
and just the history in general.
yeah, but let's not,
when we
hey, come
talk
on, dude.
about
Let's not
these
make this up.
situations,
Well, it's not
Let's not
political.
make
yeah,
It's
this a
yeah,
just
political
a
room.
factual statement.
So how much money are you making
Not
on
really
export
completely.
to the world? How much money are you making on export? And
Well, there's a
how much
choice
of
that
the
you've made.
intellectual
As a scientist,
property
you're making a choice to
historically
come
was
here.
not the US? How much intellectual not based on the historically? How many scientists
So,
did you have and
yeah.
how many innovators did you have? Who had the most patents and the most innovations in the world before World War II?
Yeah, so I can answer that. So, when you make a choice, that's a
Where
free
did it
will.
come from? Where did
Yes.
nuclear,
So,
all this knowledge come from? Where did Albert Einstein come from? From the
yeah,
US?
no. I was
No,
born in
no,
Europe. I was born in
exactly,
Europe. I
no.
was I was born in Europe. I'm an immigrant, so no issue there. But the fact is, there's a free
Oh my
will
god,
with you.
seriously?
Hey,
Okay.
Mara, you're on
So my
hot mic.
daughter,
Hot
hold
mic,
on, guys.
Mara.
I'm on Clubhouse. This
Mara, you
is
got a hot mic.
ridiculous. Oh, sorry, guys.
Yeah,
I'll be
no worries.
back. I'll be back.
But the fact is, you made a choice to come to America. That is the fact. So you could have stayed in Portugal, but when you make that choice, you
I
made the
would
choice.
get
It's your choice.
personal, and you getting to my personal life here. We are
No, I
talking
meant
what is
scientists in
happening in
general.
general.
Scientists in general. Scientists in general.
okay.
Yes,
So I just
exactly.
quickly, Katerina, I really feel for you in this situation, and this is not a way that I would ever talk to you. And yet I've been monitoring um, the same sort of happenings in the world and um, trends and everything like that. But this is an important aspect when we talk about these things. If you want to bring in an attachment to an ideology, it's going to create a form of suffering for either yourself or another person. So the attachment to the country, the attachment to any sort of ideology, this is somewhat the problem and why I think they kind of didn't really let the whole American populace know exactly what was going on because of the whole America sort of mentality and exactly how that mentality actually impacts other people that have to endure that sort of narrow-minded thinking when it comes to the global systems, all of the people around the world, and not just Americans alone, um, and all of these people, and a lot of this ideology will get then cloud a person's ability to actually see clearly. So if they're actually attached to any ideology or have any bias whatsoever, they're not going to be able to see what's actually going on in geopolitics clearly because it will be rooted to an attachment of either their own home turf or their own group or their own ideology. And to actually see what's happening clearly needs to be free from any of that. And I am only saying this because I just want to let you know, Dr. Ren, that I truly appreciate you, all of your time and energy here, even though I have talked about the escalations or the situations that seem to be escalating around the world. I by no means am attaching an ideological view to what it is that I'm watching, and I just know that other people are suffering as a result, not just in one particular country alone. And just so you know that I cherish and appreciate your time here, and please come back and please continue to talk about such an important topic, because the way in which you elaborated about what's going on was very effective and very meaningful, and very appreciative of you and sharing your time and energy. And I'm done talking. But it is very important, because if people want to actually go out there and try to do some probabilistic modeling with what's going on in the world, your attachment to an ideology will keep that from coming to fruition.
Yeah, thank you, Kyle, and I just wanted to explain. So we are talking about what happened to people that contributed to productivity to this country for their whole life significantly, with not necessarily a very high pay or anything. And we are talking about what happened unfairly to these people, and then people start switching to country general situations, war situations, intellectual property. The that person was innocent. They dropped all the charges. He went back. The lab was basically abandoned. The lifelong, very hard work that person did and benefits this country was destroyed. And it's not the only person, and very unfairly. This has nothing to do with some war or anything else. This is a personal story from a person living his whole life here, not the whole life, but a big part of the life unfairly, and was treated like this, and that is not okay. And I don't think you want to live in a country, because I guess, Americans are all about freedom and stuff, I guess. At least it's written everywhere. And we talked about safety and so on. You want to be safe in this country, you want to be free and live free. But taking current Cold War type situations to make excuses for these type of occurrences is the problem, because you always think it will never happen to you, but history tells us, and the US is not different from any human history. Thousands and thousands of years of human history shows us that this can happen to any sort of population, that people start targeting you, and this has nothing to do with the Cold War situation.
I think whatever. I didn't mean to start this political conversation. First of all,
You're fine.
I'm not. Yeah, I'm not a foreign scientist here. I'm an American. I have been American for more than 20 years. And but what I was saying is, this country has something bad is going on, which is not fair to some people. You think about it. The former FBI director Ori said that publicly, okay, said that all the Chinese are spies. I mean, you you can't make that kind of blunt, statement. All the Chinese are spies. 99.999% of the people, either they are still Chinese or they are American, Chinese Americans. They are hardworking people. They are making contribution to this country. Now I view America, because I'm an American citizen. America is my country. And then when you say that, you can't use, well, a few, if definitely each nationality this happens. A few people, they are bad people, bad apples, but you can't say all the people originated from that country are spies. That's not fair. I'm not trying to argue all those things anyway. What I'm trying to say is, I agree to give the presentation, and I feel that you guys, a bunch of entrepreneurs, what I'm trying to say is people work hard and made the invention, really should put the invention into the good use for the people. Of course, we are in America for Americans, and so how to make this happen? University, so much invention, so much discoveries, how to make it into commercialize this, marketing this into products, that kind of thing.
Yeah, yeah, I agree. It's really important. And the tiny start we are making with Science Society is at least to contribute to the awareness of the technology, invention, science that is being worked on and developed. And Mayor, he offered and is really interested here in adding to finding ways of exactly doing that. So I'm glad you're saying that, because that's exactly what we are planning somehow to do in one way or the other. We have to figure it out. But I agree that's really important, because let's say I had a speaker here, or a few speakers actually, talking about antibiotic resistant technologies to address that. And the speaker said there's enough funding for her to do the research, but then to take the amazing results she has, and that companies pick that up, it's a problem, because current antibiotics are just too profitable currently for them, and it doesn't have any financial they don't have a financial interest in taking those new technologies in, because they can just make more money with the current cheap antibiotics. So, and there's a real gap
And
there that needs to be addressed. I agree.
I just have to mention, a friend of mine is going to be undergoing two major surgeries because she had a femur implant to repair a shattered femur, and she's had problems with MRSA, right? And that molecular drill, if it could be brought to the point where it's available for patients, I mean, it would save people's lives. It would avoid a lot of suffering. My friend has been through so much with her injury and everything that followed from it, and it's not a priority for the way um, uh, pharmaceutical products are developed, but also there's real opposition to government programs to bring things forward when the pharmaceutical industry isn't interested in them, because somehow that's competition even though they're not interested in it, right? So there are things that really need improvement on every level. I did want to mention really quickly for Dr. Ren. I'm sure this is not anything you don't already know, but I think that if you could show some results with photovoltaics using boron arsenide, I think that would open up a whole lot for you.
And
Yeah,
just to say, I hope.
as far
Oh,
as the
go ahead, Dr.
crystal
Russell.
uniformity is improved, we have tried that in fact before, but the crystal uniformity was not so good, and then we did say photovoltaic effect, but it's not good yet, and we're continuing to work on that definitely. If we have some good results, I'll let you know.
Looking forward
Does it
to.
have a direct?
I think we have been going on for more than 3 hours, so I really appreciate um, your time, Dr. Ren. You have been here um, for a long time, and we had all types of discussions. I hope you really enjoyed it. I'm sure we did, and thank you everyone for coming here and making, asking, interacting, stating their points of view. I think it's important to discuss difficult topics in general and just openly and honestly discuss, and also to learn from you was a really amazing experience. And we wish you all the best, and maybe in the future we can meet again and talk about more of your projects and yeah, about future endeavors. So we really appreciate your time, and we wish you all the best.
Thank you. Thank you
Thank
so
you so
much.
much.
Thank
We
all of
appreciate you.
you so much for the opportunity to present whatever we have recently achieved on these amazing materials. And if you have any questions related to these materials, you can send me emails. I will try to answer it. I normally very quickly. I read emails very quickly and respond to every email. Basically, if it's not something unreasonable.
Okay,
Okay.
that's very kind of you, and we
Yeah, thank you.
appreciate that.
Okay.
Okay, enjoy your weekend. Happy weekend, everyone. Happy Friday. I hope we hear you all back soon. We'll have more rooms like this next week, and I'm looking forward to have more discussions of all types. So thank you so much, everyone. And
Great. Thank
Thanks,
you. Bye.
Dr. Ren.
Yeah. Thank
thank
you.
Thank you
Bye.
for the discussion, guys.
Yeah.
thank you, Ken.
Appreciate y'all. Thanks for having this space.
Thanks. Bye. Bye, everyone.